faculty members, research scholars, and dear participants. It gives me immense pleasure to welcome you all to Day 2 of the International Conference on Emerging Frontiers in Sustainable, Functional, and Advanced Materials IC-SFAM 2026 being organized by Physics Department of Shivaji College. As we step into the second day, we continue our journey of exploring innovative ideas, groundbreaking research, and meaningful discussions in the field of sustainable, functional, and advanced materials. We are truly grateful for your enthusiastic participation and presence, which adds great value to this academic gathering. Now, moving ahead, we begin with session 4 of day 2. We are honored to have with us Professor Jai Singh, University of Delhi, who will be chairing this session. It's my privilege to introduce our esteemed chairperson, Professor Jai Singh. He is currently serving as a professor in the Department of Pure and Applied Physics at Guru Ghasidas Central University, Bilaspur, Chhattisgarh, and is also associated with Department of Physics and Astrophysics, University of Delhi. Professor Singh completed his PhD from Banaras Hindu University in the field of oxide nanomaterials and has carried out postdoctoral research at prestigious international institutions including Germany and South Korea. His research areas include nanomaterials, 2D materials such as MOS2 and energy materials. He has published over 150 research papers with significant citations and has received several national and international fellowships and awards. We are truly honored to have him with us today. I now request Professor Jai Singh to kindly take the chair and conduct session 4. Now it's my honor to proceed with the felicitation of our esteemed chairperson, Professor Jai Singh, as of our respect and gratitude. Now we request Dr. Neeru Sharma ma'am to felicitate Professor Jai Singh with token of appreciation by presenting him with a shawl. I now request Professor Jai Singh to kindly take the chair and conduct session 4.
Thank you very much. Please give me podium program. Okay. Thanks to Shivaji College, the organizer of this conference, and firstly, first talk Professor S.K. Sarman sir from Meerut University. He will talk about the novel metal modified porous nickel foam. Very important topic. The CO2 right now, that is sustainable, and that is very important topic. So okay, he is not mentioned in the brief about this. So I request him to introduce sir. Thank you.
Thank you very much, the chairperson and the organizing committee who invited me and gave me a chance to share my learning here in India and abroad. So, I am a professor since 2018, Chaudhary Charan Singh Viswavidyalaya, Meerut. Before joining the university, I worked in South Korea more than 12 years. So today I am going to discuss about environmental and aquatic pollution, what is the major deficiency in our systems we have created. That was not earlier, but we have created. So there is a snapshot some of my universities. So I think the pointer will not work, this one. So my universities, NIRF rank is 17 state universities and all over India in 38. So these are the brief profile of the university. So these are the variety of ranks in the last 5 years. So these are also in the category of QS ranking. And here the important things, this is my slides. The left side, the publishers where I published my articles. And the right side you can see the yellow one highlighted, my articles last 2 years. So in the material science engineering reports and carbon energy is recently published last week. And coordinate chemistry review, materials today, Infomat, small, and so on. So these are the collaborator and partners, my universities, globally, national, international. We are sitting here in a well-established capital and the college, and we are sitting in the well-organized auditorium, well-equipped auditorium, well-civilized citizens, but still we need to further study. Why we have to? That we have created in the last 50 years. So the two types of contamination is there. In one thing, in the edible things, another thing, the environment. So environment is the carbon dioxide and carbon monoxides and other noxious gases and contamination. So here the polluted edible things. If we test any of the material in the market available, we can find the heavy metals, variety of heavy metals that it is to the edible things and develop. So that's why we need to develop some functional and smart nanomaterials. Other things like global warming and poisonous environment, and need to develop the sustainable systems for effective CO2 utilizations. I think here some research scholars and students, I would like to ask, what is the most the dangerous gas in the environment? Can anybody? The students? I think nobody. That is the carbon monoxides. So what is the source of carbon monoxides? Every ignition system, including the gas stove, including the home, the gas stove, and any kind of ignition, the vehicles, the industries, and any kind of boiler. So any kind of, even the wood, the coal, so everywhere it is emitting the carbon monoxides, one of the toxins. So harnessing the nature power to empower our planet, that important thing. The environmental protection, that is also written in the Vedic culture and philosophy. That means sanchalam hi mana krishna pramati balavadadam tashamam nigramane vare dusukram asansam mahabano modusi chalat abhyasantu konte vragyan जय। ये हमारी भागवत गीता के 6ठे अध्याय में 34वां वर्सेस है. That is well written, but we have not the highlight that one, not the very variety of misinterpretation the many times. The meaning is this: today everybody talking about the environmental sustainability, the environmental cleaning, the contamination, then air contamination. Somehow people say the Delhi is just in the air globe. It's too much polluted. So it is well written. The environmental mental consciousness is compatible with each other. The more the mind is pure, and the more the pure is the environment. यदि हमें environment clean करना है, तो first of all we have to think about the pure of our mind. So it is written, as studied in the Vedas, the purification of mind is the first step for purification of the environment. पहले हम अपने दिमाग को ठीक करें, तब हम environment को ठीक कर सकते हैं. इसका मतलब ये है शुद्ध. And according the Astropnisad, it is the universe made of the 5 important things that is we call the Bhagwan. That means the air, sky, water, and the fire. In the fast developing globe, we are focusing the development. Today, the 2 most important development is the touch technology and the voice technology that we have developed it. Everybody behind the hi Alexa, please sing a song. Hi Alexa, please this song. Hi Alexa, hi Bixby, call this one, right? So everywhere the voice sensors come working. Second thing, the touch sensor. Those sensor was existed the 1,600 years back as well. We haven't think it. So we have just, because the rulers trained us that we have to follow the Western's development, not the ours. The 2 most important stories, I just give you the brief. One is the Aladdin ka Chirag. That means touch technology. You can compare your touch technology your mobile phone. Second things, the Alibaba Chalis store, that was the Khulja Sim Sim Band Ho Ja Sim Sim. That means that was the voice sensors. The voice sensor was there. That means the voice sensor storage system was there. That means they have preserved the voice of that particular person. The voice sensor, the memory is there. The memory is there, that processor is there. Microprocessor, because that is the process. The microprocessor is there, then the door will open, the door will close. That means mechanical motor is also there. Without mechanical motor, we cannot drive, we can move any kind of gate. So two technology we had in the past in India, an Indian subcontinent zones, the touch technology and voice technology. Today we are enjoying the 21st century the same. So we think about the development. So development we had in the past, but we haven't preserved it. So that's when we have to go for the research and development that we are discussing today. Everywhere, the environmental sustainability, avoiding toxic materials for health prevention. So that means prevention better than cure. So we are working the what kind of prevention? So that we have everybody running behind the smart home, smartphone, smart class, and everything is smart. And we haven't the smart. You know, smartness can work. If you are hungry, then smartness cannot work. You have to go the food stall and then you have to take it and you have to eat. That is physically no way that any smart technology can work. So that means that is the Alexa is the example of the voice sensor. So and the automations everywhere. Even I am enjoying at my home that same one. You know, I'm thinking about the contamination in 2012 when I was South Korean just a professor. So these are the sources, the four kind of sources. We are very, very highly qualified, mostly doctorate and masters and bachelor students. We usually wash the clothes in the washing machine. We are very happy that we have cleaned the clothes. But how much you are contaminating the environment? You know, all kind of detergent have the sulfate or sulfides. Google में डाल के देखना, these are the toxic. Means how we are contaminating the environment. That means we have to avoid the use of detergent as well in the near future. If we need a clean Yamuna, especially in Delhi, so we have to avoid any kind of detergent. We have to find the other solutions. So here that is already published in one of my review articles, the Materials Today Sustainability 2023. So here we checked the 12 water. 12 water, you know, the heavy metals contamination 10 ppm acid well our body, 10 ppm. But you know how much? 100, 200, 300 ppm is there. Water is clean, but heavy metal is there. Many of the students, I think, did not awareness the RO water, the TDS. What is TDS? TDS means the dissolved solids, total dissolved solids. So that means whatever we are getting the outcome, that is contaminated. The seafood is also contaminated. Not only in India and South Asian countries, it is well contaminated in Japan and South Korea as well, Singapore as well. So whatever they are preparing the seafood, they are means harvesting, they are forming the different clean water zones and not in the sea, because sea water is completely contaminated. So this is my plan. I was thinking and I just make this sketch and this schematic and finally published. Another thing, we are talking about the CO2. You know, this article is discussed about the CO2. I think Dr. Neeru Sharma is also the co-author of this articles, Materials Today Sustainability. So we are working how to control the CO2 and CO. So that is Materials Today Sustainability. We have mentioned, so what kind of source, how to control and how to convert the different forms. You know, CO2 can be utilized in very efficient way in many ways. You know, CO2 can be used as a preservatives, CO2 can be used as the production of the urea, CO2 can be used for other kind of medical treatment as well. So, but the awareness is important. So these are some survey. So I will skip the survey about here. This is important slides. You know, the highest contamination of emission of CO2, the country is China. You know why? You know why? Because of maximum number of industries. So every industry, you know, every irrigation system. That is last year there was a call from DST, NRF. That means they have a special call for CO2 reduction. I applied that project. I don't know what will happen. So I mentioned this one because I am working since last 5-6 years to CO2 or CO reduction. for the efficient and valuable products that is not contaminated. You know, and the least is the Australia. That Australia is not for technology, it's for the dairy farms. And you can say USA, India is also second, third largest the CO2 emission. So this is already published my data in Materials to Sustainability in 2024. This is another articles in especially in Materials to Sustainability in 2024. So here also we discuss about the CO2 detection depends on multiple factors, the chemical composition, temperature, humidity, morphology and crystal structure. So these are the means the materials we are using about the control of the CO2. So you know we are leaving, we have suggested in the final the perspective of articles the detection and the conversion. The quantum histochemical catalytic materials for selective multi-carbon building products. This article is just published last month in the month of Materials Today Physics. So this is very important articles. The published pages are 54. So this is very interesting articles, and we have mentioned the variety of 2D materials, and that means sources and the effects and the products and the conversion. So this is the third articles in the queue, 23, 24 and 26 about the CO2. And we also developed some kind of catalytic materials for CO2 detection as well. So this is a timeline. You know, the publication is not important. The important is the information. The journal name is not important. The journal, the awareness is important. So here we mentioned the about 1902, the where we were and what kind of material we were using, and we also recommended and suggested about 2050. So these are the just expectations. That's my thinking. So next 20 or 50 years में what क्या होने वाला है. So उस तरह की just timeline. So you can find my every article in timeline the same process. So these are the some survey about the CO2 with respect to the years, and here we also mentioned the variety of materials in these articles and how to use them, how to make the efficient materials. And you know, important thing is that if we are using the different material, but material is toxic, so that is not important. So we are considering the materials after using should not be contaminated. You know, we are using the gallium arsenide chip. I never ever seen in India that every qualified citizen the disposing the battery chip in the right place. I never ever seen. While the government of India have well established the rule and regulations, so nobody is following. Think about, while the battery is discharged, what will do? Just throw in the garbage. Garbage, what will happen? The battery usually made of lithium, lead sulfide, cadmium sulfide, lead mercury, and so on. So these are the heavy metals. The heavy metals where are going to the drainage systems? We are piling in the कचरे का ढेर में डाल रहे हैं, वहाँ से क्या होगा? डिसोसिएट होगा, डिसोसिएट के बाद बारिश के थ्रू वो ड्रेनेज में जाएगा, ड्रेनेज से कहाँ जाएगा? इरिगेशन में जाएगा, इरिगेशन से we are coming, that is cycle. So we are eating heavy metals. What happened today? That number of disease increasing. The number of recently we have published in ACS Applied Nanomaterials one recent articles. So we have mentioned clearly mentioned what happened, the heavy metals accumulation in the body, the developing the cardiovascular disease. This is my recently project NRF with Delhi University 2.3 crore. So we are working this project. So we have mentioned the heavy metals, how it is coming to the food chain and what is happening in the body. So we mentioned very clearly, very good articles. It's about online 1 or 2 days, next 2 days. So that is the CO and CO2 materials. These are my perspectives about these articles. So role of microstructures. So we have mentioned, you know, today we can see have 4 kind of microstructures. The 0D, 1D, 2D, 3D. I have tested all. I have developed myself all kind of microstructures, and I have tested all. And finally I concluded that we have to go for nanotube, not nanowire. The last slide you can see, you know, the nanotube have the large surface area and the single traps to transfer the charge carriers. That's why this is one of the Japanese research, and I'm citing this one last 1 decade. Everywhere I'm citing this one, why I'm working the nanowire and nanotube. So because we tested all, and all the different microstructures published different articles as a research article. So then when photokinetic performance, we have tested first the carbon nanotube. The carbon nanotube is one of the most efficient. You know, carbon tube is not dangerous. After working, it will not damage the environment. कार्बन ट्यूब हम आंखों में काजल डालते हैं, उसमें भी कार्बन ट्यूब हो सकता है. हम तंदूर की रोटी खाते हैं, जल जाती है, उसे हम खा लेते हैं, काला होता है, वो भी कार्बन ही होता है. हम बहुत सारी चीज़ें खाते हैं, हम कार्बन नॉट डेंजरस. हमारी बॉडी जब डिस्पोज होती है तो मैक्सिमम 2 टाइप ऑफ मटेरियल्स बचते हैं, एक कार्बन और एक सिलिका. सिलिका हमारी अर्थ क्रस्ट में 68% है. एवरीवेयर इज सिलिका. द वुड, द हार्ड इज द वुड, द मोर सिलिका इज देयर. इवन द जो गाड़ी के टायर होते हैं उसमें 68% सिलिका मैंडेटरी है. 68 से 73, 75 तक जाता है. दैट द वेरिएशन द ब्रांड ऑफ द टायर. सो सिलिका इज टू इम्पोर्टेंट मटेरियल. So we tested about CNT and TiO2. CNT, TiO2. Titanium dioxide is one of the most the catalytic material for clean the water. So we tested about 3 kinds of structure. This already published in one of my PhD students, IC-SFAM. So this kind of structure we have developed in our laboratory. You can see the kind of gande ka flower hota hai, but this not that flower. So I have given the different name, the purple Instagram flower. So it's completely matched the naturally. So we are producing the microstructure as well, what is the nature is developing. So we are trying to focus, our research should be match the nature as well as the development as well as the treatment. So second things, while we have included the CNT with the titanium dioxide, so we have established the CNT TiO2 nanospheres, and we have filed 3 patents, all 3 granted. So now we are working for the development of a system. So first we have treated several times repeated. So that is that's accidentally or the one time, or we can fabricate anytime. So we find many times, every time we find the nanospheres, uniformly developed nanospheres. So you can see the high resolution, low resolutions. And finally, we have got the patent in 2023. So these 3 types of photocatalytic reactions. You know, photocatalytic reaction is one of the important. जब मैं PhD करता था ड्यू में, तो कई बार बस से निकलते थे, तो इधर गुरुद्वारा पड़ता है वजीराबाद की तरफ, तो वहाँ वाइट मिट्टी से डालते थे ट्रक में ला के. तो उस समय मुझे नहीं पता था क्यों डाल रहे हैं. दैट वाज द टाइटम डाइऑक्साइड. मिनरल्स है, ये माइन से निकलते हैं और वहाँ डालते थे, उसके बाद वाटर साफ होता था, लेकिन वो थोड़े दिन बाद बंद हो गया. तो टाइटम डाइऑक्साइड हमें गंदे पानी में डालना चाहिए. लाइट के जब लाइट डलती है तो ऑटोमेटिकली क्लीन हो जाता है वो. और टाइटम डाइऑक्साइड कंटेमिनेट नहीं करता है एनवायरनमेंट को. जितने भी वाइट पिगमेंट हैं पेंट्स के, वो टाइटम डाइऑक्साइड है. टाइटम डाइऑक्साइड सबसे ज़्यादा यूज़ होता है जो सन क्रीम्स होती हैं, उसमें यूज़ होता है, क्योंकि सन क्रीम में क्या है, उसका बैंड गैप 3.2 होता है, तो यूवी लाइट उसमें बॉडी में पेनिट्रेट नहीं करती, और बायोफिल्म जो डिपॉजिट करते हैं उससे हम प्रोटेक्ट करते हैं अपने बॉडी को एज वेल. सो दीज आर द मैकेनिज्म अबाउट वर्किंग. This article already published in Social Science. Second thing, when we tested titanium dioxide, then we started testing the zinc oxide as well. So zinc oxide, and I included the yttrium. Yttrium stable the material. That I have done in my postdoc research. What is the role of yttrium in the material compositions? So yttrium is working, the 6 kind of microstructures I developed in my laboratory, and finally this article is published in Materials Today Chemistry. So these are the outcome of, though we have concluded the different the exposure of the light and different kind of treatment of the contamination. I also got 1 Korean patent. Then I started, why not other materials, carbon-based materials we should use? The main is graphene, CNTs, single wall CNTs, multi-wall CNTs, and graphene oxide as well. So I tested all material. Why either CNT is working, graphene is working, another material is also working. So we tested the nanosphere about TiO2, CNT, single wall CNT or multi-wall CNT. So we got the multi-wall CNT. So we have established each and every materials, and finally we concluded this one, the material. You can know, we have tested a single tube. I checked means the diameter inside or outside as well. And how the single wall, the multi-walls, and the graphene, and TiO2 nanoflower, TiO2 single wall multi-wall nanospheres, and the TiO2 multi-walls. Multi-walls में nanosphere proper तरीके से नहीं बन पाएगी. These are EDEX mapping. So we have completely established the material, it is working or not, and finally we have submitted this to the Journal of Environmental Chemical Engineering. That was not published in the journal. It is Yeah. So this is important slide. Important slide is that we have produced the single wall TiO2 nanospheres, and then we have coated on the cotton textile, and then we treated the water. So this is very popular and very established the research. On the behalf of the research, we are developing some prototype system. So that research very popular in live and print media as well. So we also got the patent for this. We got patent in 2023. Now this is the mechanism how it works. The textile. You know, textile membrane is good, but it's certain limitations because somehow the drainage water have the acidic nature. That time that it will not work. So we thought how we overcome if the acidic nature of the water. That we have started the nanosponges of the metal nanosponges. So different kind of metal nanosponges, we will discuss about it. So this article already published in Diamond and Related Materials. And another article, the same thing, the graphene about metal science engineering B. So electrochemical conversion CO2 to value-added chemicals. This work is performed one of my students during the international collaboration, India and South Korea. So I sent my student for 1 year, a student access program, and he performed that work over there because they have well-established laboratories. So we have used three kind of novel metals, the gold, silver, and palladium, to modified hierarchical and the porous nickel forms as a catalyst. So this kind of nickel form can use for any kind of drainage water to treat the water. Why nickel form? So high surface area, 3D porous structure for more active sites, good electrical conductivity, essential for efficient electron transfer in electrochemical the reaction. That is important. And the mechanical stability can witness the long-term heterogeneous conditions. Chemical compatibility is stable under reduction conditions, especially in aqueous and organic electrolytes. The role of CO2 reduction enhances the electron transport and the effective overall the catalytic reaction. So we have completely converted put CO2 to dimethyl carbonate. So there was a question, while we are reducing the CO2, it usually forms the carbon monoxide that is more dangerous than CO2. So this is the important and the quality of this work. While we have tested several times in situ measurement, while we are CO2 we are reducing that CO is very minimum amount. So that is the quality of this work, and we have reported this work in the Nature. So it's about to come. I don't know when, because they asked many revisions. So this is on the process. So this is the quality of the work. This is completely experimental process we have performed. Not a very complex, very simple way we have defined it. And finally, we have the real-time experimental images of electrochemical DMC, dimethyl carbonate reduction. That is the useful material for the environment and for the variety of things. So we have tested different ways. We haven't leave any kind of things. We haven't left anything. What the ways, the possibility, we have completely established. No other way that somebody raised a question that you have not touched this way, you haven't touched this way. So everything, you know, the supplementary is 56 pages. Supplementary. So, and simulation as well. So simulation is giving the before activity and after activity, before and after treatment. The post-treatment, pre-treatment, we have done it. So core level experience analysis as well. So we find even we have this some treatment, hydrogen treatment, the before treatment or after treatment. We tested both sides. There is no big impact as well. So after treatment and before treatment, there is no big impact. It means it is compatible in the toxic and flammable environment as well. That experiment defined. So in conclusion, the successful and relatively uniform deposition of silver on the hierarchical nickel form surface. So we tested three metals. So silver is giving the better than gold. Even gold is expensive. So silver is quite good. So this filter, now the next phase we are going to test how long this filter works, how many cycles we can use this kind of filter. Because this kind of filter we can use variety of applications. So the reaction time that we have mentioned here, the cathode carbon electrolyte and silver hydroxide nickel form, so the limited CO production, that is important. यदि हम CO को ज़्यादा प्रोड्यूस कर दें CO2 रिडक्शन में, that is more toxic. The intermediate products are more dangerous than the primary product. So we have focused this one, so very limited that one. You know, here you can see the three kind of product, the CO, the silver foil, and we can see the response. So we have tested silver hydroxide nickel form. The silver form is maximum, and the no electrode is no the hydroxide nickel form, and the best performance about silver functionalized hydroxide nickel forms. So higher current density observed in silver functionalized hydroxide nickel form indicates a better electrocatalytic activity for CO2 reduction. We have to work in Delhi as well, because the large number of ignition system on the road and at home. I checked last week the percentage of contamination. You know, the 18% the kitchen emissions, 18%, 26% of vehicles, 40% the construction industries. So these kind of contamination we are not focusing. The government is focusing just on vehicles. Of course, the vehicles are emitting the CO2 and CO emissions, but not everything is the vehicles. So I think the government should change the focus. So there is a need to develop the sustainable system for effective CO2 utilizations, electrochemical conversion of CO2 to DMC in the presence of a catalyst, and modified hydroxide nickel form as a working electrode as an effective approach. This structural electronic modulation significantly enhance the catalytic performance, achieving the high DMC Faraday efficiency of 86.2. It is the maximum highest ever reported. Maximum reported earlier it was 76. So this is the highest ever today. So DFT further really into the hierarchical structure, the normal but incorporation notably lower the energy barriers of SCCO formation and subsequent steps, thereby accelerating the overall DMC synthesis pathway. So I just give some highlights. So materials today chemistry, about 2 articles in a row. You know, when I publish the article, I choose the same journal. That means the next work, the next step, that is indicating, not the different journal. So usually I focus the variety of journal. Materials today sustainability, so 23, 24. Materials today physics in 25. And materials today physics in 26. So impact factor about 9.7. And this is my laboratory where I worked about silver nanoparticle lens nano and other things. You know, these are 2 images are important. The left one, the current applied physics in 2018, I developed the silver gold nanoparticle functionalized in nanosponges, zinc oxide nanosponges. The right were the gold functionalized nanosponges. 2 different. So both different journals recently published. I developed these nanosponges in 2017, but due to the migration to university, it is delayed to public. You know, while IIT Bombay reporting 2023, they have developed the nanosponges. So one more article in the catalytic reactions in small. And last year I got 4 patent granted, 5 granted, 5th one is not here, 4 granted. And 5 published and 5 granted last year, 2025. So these are the some the media, print or live media coverage. Even when we developed the CNT TiO2 nano spares coated the textile membrane, it was very much highlighted in print media, live media, and finally the Yogi ji also tweeted the natural purification methods ensure the reworkingless saves crores Yogi Adityanath. He also quoted my timeline. So these are, you know, intermediate product of carbon monoxide is also dangerous as well the CO2. So here we worked about the CO2. So we have developed some nanoplum, and some of the co-researcher is our team, Dr. Neeru Sharma. So she developed, and now that girl is working PhD in South Korea from last 1 year. She moved to South Korea. So in my conclusion, I usually have very small concluding remark. That means हमें क्या है, किताबें रट के हम पढ़ के नंबर डिग्रियाँ ले ली हमने, लेकिन जब कुछ पूछते हैं फिजिकली तो हम बिल्कुल गुल हो जाते हैं. हम 90% नंबर लाते हैं, किसी भी एंट्रेंस में 25% लाने के योग्य नहीं है. तो हमारी जो प्रॉब्लम है वो बुक की जो लाइफ है हमारी अलग है और जो रियल लाइफ है वो अलग है. व्हेन यू स्टार्ट द कनेक्टिंग योर लाइफ, द बुक लाइफ और रियल लाइफ, दैट यू विल रियलाइज you will never ever the memorize it, just understand it. That means किताबें पढ़ना ही ज्ञान नहीं है, किताबी ज्ञान को सांसारिक अनुभव से जोड़कर देखना और सुनना समझना ही स्व अनुभूति असली ज्ञान होता है. वेरी छोटा रिमार्क है. We also work in other articles as well. We also working the devices, the Materials Today 2023, and another article 2025. This is carbon monoxide. And other devices we also develop working on the photo detector as well. The photo detector, one article published in Materials Science Engineering R, and another article in 2026. This is by factor 3.16. And I also received 3 awards last year. One award, the Pride of the Meerut, organized by the Hindustan. And this is one award from my merit, my pride. And I also got the best professor award from my university. It is just given the one award since it was from the means established, and luckily they choose mine. So thanks my university and all the leaders of the university. I also got, when I was working in South Korea, I also got the best professor award 2012. Here you can see 2012, 30 of March. So these are the acknowledgements: the University Grant Commission, the ANRF, DRDO, and UP Higher Education, and St. Cubilis Center of Excellence, and CSTUP. So these are the funding agencies, and these are the acknowledgement and my co-research team where we are working. Thank you very much. I think I finished my time.
Thank you, Professor S.K. Sarma sir. He speak very nicely about the CO2 reduction. So definitely we know about the basic about this work and then how to utilize and then save our society and environment. Okay, now session is open for the question.
You are converting from ethanol to DFC room temperature or
Room temperature.
what's the catalyst?
Catalyst, yeah, nickel form. Silver functionalized nickel form. Nickel form we purchased from market any time. So helical we have functionalized and we have coated the silver nanoparticles. Because the toxic environment, the textile membrane cannot work.
Sir, like you said that we can use titanium dioxide to clean water and remove the heavy metals. But is it safe to use titanium dioxide or?
We cannot remove the heavy metals. To treat, to eliminate the heavy metals, there is another process. I told that Ti2 is one of the best catalyst, especially photocatalyst. So we can remove the contamination, we can break the molecules, the dye molecules, the antibiotic dye molecule, because the discharge of antibiotic one of the biggest issue today. Antibiotic not only the humans but are the crops. हम क्रॉप्स में पेस्टिसाइड डाल रहे हैं. पेस्टिसाइड क्या है? दिस इज आल्सो एंटीबायोटिक फॉर पर्टिकुलरली हर्ब्स और पर्टिकुलरली बैक्टीरिया और पर्टिकुलर इंसेक्ट्स. सो दिस आर द एंटीबायोटिक. सो एंटीबायोटिक इज कमिंग इन द फूड. Antibiotic is not only food, the drainage system also going to the drainage system. So antibiotic is impacting the more. When I was in South Korea, I watched one movie. One professor like him, he was working in laboratory, he was passed away, so laboratory was closed for 30 years. Nobody opened the laboratory. But the next professor, they allotted the new laboratory. What they did, all chemicals they drained in the drainage system. That drain system go to the sea. And sea में fish को जब consume किया वो तो monster बन गए वो. 80s की मूवी है, 80s 90s में बहुत पॉपुलर रही है. तो हमें किसी चीज़ को भी, कल मैं एक लेबोरेटरी में गया तो वो जो केमिकल यूज़ करें वो नाली में डाल रहे हैं. नाली में नहीं डालना हमें कंटेनर भरना है, उसको डिस्पोज कैसे करें उस पर काम करना है. तो हमारा काम बिगाड़ना नहीं है, हमारा काम जो मैं रिसर्च कर रहा हूँ वो सुधारने पर है. तो उसको कैसे डिस्पोज करना है, चाहे वो बैटरी है चाहे वो वेस्ट है. अभी एक मैंने रिसर्च किया है, उस पर देखा है जो गैलियम आर्सेनाइड चिप करती है, हमें क्या चाहिए, मोबाइल चाहिए, फास्ट फंक्शनिंग चाहिए. नहीं कर रहा तो काम नहीं करेगा। जो स्लो मोबाइल हैं वो सिलिकॉन बेस्ड हैं, दैट नॉट डेंजरस। जो फास्ट मोबाइल हैं वो गैलियम आर्सेनाइड बेस्ड हैं, और जब गैलियम आर्सेनाइड चिप खराब होती है तो फेंक देते हैं। तो जब गैलियम आर्सेनाइड आर्सेनिक एसोसिएट होता है, डिसोसिएट होता है इससे, तो क्या करता है वो, आर्सेनिक यदि बॉडी में आ गया तो किसी भी दवाई से ट्रीटमेंट नहीं है, उसका मरना तय है। तो वी हैव टू टेक प्रिकॉशंस, तो वेयर वी आर यूजिंग द गैलियम आर्सेनाइड चिप एंड हाउ टू प्रोटेक्ट दैम। तो मेरा क्वेश्चन क्या था, द प्रिवेंशन इज बेटर देन क्योर, द स्टार्टिंग माई लेक्चर। तो हैवी मेटल्स उससे एलिमिनेट नहीं होते हैं, हैवी मेटल्स डिटेक्ट कर सकते हैं, लेकिन एलिमिनेट क्या होता है, जो टेक्सटाइल मॉलिक्यूल्स हैं, हम सभी रंगीन कपड़े बैठे हुए हैं, 30% जो डाई है वो ड्रेनेज में जाती है 30%, 30 से 40%, 60% टेक्सटाइल या फाइबर हमारा कंज्यूम करता है। जो फाइबर है, जो फैब्रिक्स हैं, ये वैरायटी ऑफ फैब्रिक्स हैं, मैक्सिमम 60% कंज्यूम करता है, 40% ड्रेनेज में डालते हैं। तो हाउ डेंजरस, डाई मॉलिक्यूल मुंह में जाएगा तो क्या होगा, और हम ड्रेनेज में डाल रहे हैं, ड्रेनेज कहाँ जा रहा है, वो आपके पालक में आ रहा है, आपके करेले में आ रहा है, आपके तोरई में आ रहा है, वो क्या करेगा, आपको कैंसर बनाएगा ना, आपको बीमारी करेगा, आपकी इम्यूनिटी खत्म करेगा। तो हमें फूड चेन में जो है उससे बचना है, दैट वी हैव टू वर्क फॉर प्रिवेंशन बेटर देन क्योर।
But the thing I want to ask that is titanium dioxide is safe to use or
safe.
not? And if, are there any drawbacks of using titanium dioxide or not?
नहीं, ड्रॉबैक तो कुछ नहीं है इसका। हम जितनी पेंट इंडस्ट्री है इज़ वेरी चीप मटेरियल, वो तो एक्सपेंसिव तब होता है जब फाइनल प्रोडक्ट में होता है। इट्स अ माइन, इट्स अ मिनरल मटेरियल, जमीन से निकलता है, जैसे कोयला निकलता है ऐसे निकलता है।
As you said that it's a mineral and it is found in the earth. But
Of course.
how abundant it is that we can use it?
This is the awareness. This is the awareness.
Okay. That's the question I wanted to ask.
Yeah.
That here are
Yeah.
there any drawbacks or?
Till now, we have developed the sensor, heavy metal detection sensor, different of materials we are using here. The silver nanoparticle, gold nanoparticle, encapsulated with zinc oxide, titanium oxide. Now we are developing the electrode, how to eliminate the heavy metals. Once we drop the electrode in the prepared food, and we can check how much contamination, it is eatable or not, check, and then use another electrode, then where the electrochemical reaction we can remove the heavy metals. Heavy metals removal is electrocatalytic or electrochemical reactions, not detection. Detection हम कर सकते हैं optical भी.
Thank you so much, sir.
Thank you. We are a little late, so if you would need ask some more questions then during the lunch time. Okay.
Thank you.
Now I request our esteemed chairperson, Professor Jai Singh, to felicitate Professor S.K. Sharma by presenting him a potted plant. A memento. And a certificate.
Okay, thank you very much, Professor Sharma. Again, we have Ananda Sharma. Okay, Dr. Mahesh Kumar Sharma. He did PhD from Delhi Institute, and right now he is a senior principal scientist as a professor in a headquarter of Delhi CSR lab, and he has more than 15-16 years research experience especially in advanced materials physics, and he has included hardware technology and 2D materials, organic electronics, surface, very wonderful areas of research, and he is actually involved in the several national major projects, basically CSIR, hydrogen technology and energy technology, and he has published more than 150 research articles in various international journals. And also he is producing several PhD scholars. So I am requesting you, Professor Mahesh Sharma sir, please speak about you.
Thank you very much, sir, for the introduction, and thanks to the organizers, especially in
Professor Neeru has invited me and asked me to deliver an invited talk. So I had been working in NPL, National Physical Laboratory, just few kilometers away, hardly 8 kilometers away from here. You may visit, or some of you might have visited this lab for 20 years. And for last 3 years, I am in CSR headquarters and managing all energy related projects. Also, I am a professor in ACSIR, and ACSIR is our academic wing of CSIR, where 7,000 PhD students are registered. So every year we give around 1,000 PhD to students. And ACSIR, I would like to introduce one important thing about ACSIR. You may be interested, all of you youngsters, that we have introduced one industry-oriented PhD program. So generally, when you do PhDs in academic institutes or universities or like in CSIR, we ask how many publications you have gone through and how many publications you have made. So this is a special program in ACSR we have introduced 2 years back, and where we are not asking any publications. We are asking you to work on the technology oriented programs. You can file patents. So if you submit one patent, you are eligible to submit your PhD thesis. And we give a special fellowship to these students, and they also have the opportunity to work in the industries. So hardly very few students have got the we also didn't receive any industry exposures, and nowadays it's changing scenarios, like people are going for entrepreneurship, startups and other things, and industries are also want to have these highly skilled PhD scholars for their high profile jobs, and they all have special R&D centers. So this is one of the ACSR PhD program. If you happen to have some motivation to join this program, you can apply. It's open to all. So let me come to my topic. So this is ultra fast light matter interactions, and from fundamental dynamics to functional devices. So ultra fast dynamics and light matter interaction, you all know that when light photosynthesis and all these processes you are aware of, and Einstein's photoelectric effect, everybody knows it. So this is the light matter interaction in the ultra fast regime. So what is ultra fast? So this whole talk is divided into two parts. One is completely basics for the understanding of the students, and one for the learned people who can to whom I can show some of the results. So whenever you want, I can stop anywhere. So ultra fast is a time scale. For example, if I ask the backside students to come forward, how much time you can take? 20 seconds, 30 seconds maximum. If I ask you what can happen in just 1 second, what can happen in 1 second? Can somebody tell? बोलो भाई, बैठने के लिए थोड़ी आए हो. 1 सेकंड में क्या हो सकता है? 1 मिली सेकंड में क्या हो सकता है? आप सिर्फ अपनी पलकें झपका सकते हो. माइक्रो सेकंड्स में क्या हो सकता है? जस्ट इमेजिन. देन माइक्रो सेकंड के ऊपर नैनो सेकंड्स है. नैनो सेकंड्स में क्या हो सकता है? देन नैनो सेकंड्स के ऊपर पिको सेकंड्स है, फेम्टो सेकंड्स है, ऑटो सेकंड्स है. ऑल दिस टाइम स्केल्स आप सभी ने टेक्स्ट बुक में पढ़ रखा होगा. बट वी रियलाइज दिस टाइम स्केल्स इन आवर लैब, and generally I work in femtosecond time regime. Femtosecond means 10 raised to power minus, बोलो, minus 15. तो 10 raised to power minus 15 की स्केल में हम लोग काम करते हैं, जो कि 10 raised to power minus 12 तक जाती है. तो 10 raised to power minus 12 से 10 raised to power minus 15 के स्केल्स में जितने भी प्रोसेसेस होते हैं वो सब हम स्टडी करते हैं. और मैं लास्ट साइड सर के से शुरुआत करता हूँ कि सारी नॉलेज बुक्स में नहीं होती हैं. कई बार जब हम बोलते हैं और हम इधर उधर लिटरेचर पढ़ते हैं, वहाँ पर भी बहुत सारी कंसेप्ट्स आपको मिलेंगे. और इस टॉक में आपको बहुत सारे ऐसे कंसेप्ट्स मिलेंगे जो आपने शायद टेक्स्ट बुक में ना पढ़े होंगे, ना कभी पढ़ेंगे. जब आप पीएचडी करेंगे या रिसर्च करेंगे तब आप यू विल कम अक्रॉस दोज कंसेप्ट्स. सो अल्ट्रा फास्ट टाइम स्केल, सो उसी को मैं रियलाइज़ करता हूँ. जैसे सर ने बताया कि इन्होंने TI2 के नैनो फ्लावर्स बना दिए. तो इंसानी दिमाग जो है खुरापात करता रहता है कुछ ना कुछ, और स्पेशली जब साइंटिस्ट एंड प्रोफेसर्स हैं उनके दिमाग में कुछ ना कुछ खुरापात चलती रहती है. तो जो नेचुरल चीज़ें हैं वी ट्राई टू मिमिक दोज इनटू अ रियल वर्ल्ड एप्लीकेशंस. जब हमने टेलीफोन, हमारे पास लैंडलाइन थे तो हम सोचते थे कि एक वायरलेस सिस्टम होना चाहिए जिसको हम कहीं पे भी लेके चले जा सकें। आज हर किसी की जेब में एक मोबाइल फ़ोन है। आप कहीं से कहीं तक भी, पहले हम अमेरिका बात करने के लिए सोचते थे कि यार पैसा लगेगा, आज हम 2 मिनट में अभी कॉल मिलाएंगे, व्हाट्सएप कॉल कर सकते हैं, बहुत सारी चीज़ें हैं। एंड एआई का टाइम है। आप पहले गूगल सर्च होता था, अब आजकल एआई सर्च हो गया, चैट जीपीटी वगैरह सब चीज़ें होती हैं। गूगल सर्च में एक लिमिटेड वो था, आपको 1 मिनट में या 30 सेकंड में आपको रिजल्ट्स देता था और वो लिमिटेड रिजल्ट्स देता था। चैट जीपीटी में क्या करता है वो, इन जस्ट 2 और 3 seconds it give lot of informations. So that is the benefit of working on the ultra fast time scales. In very short time it gathers lot of informations. Lot of informations means in just few nanoseconds it gathers gigabytes, petabytes type of data it can handle. So all this happens because हमने खुरापात करी और हमने सोचा कि जो नेचुरल फिनोमिना है उनको हम रियल टाइम में कन्वर्ट करके दिखा दें सबको. So here in this slide you can see there are a lot of natural phenomena which occur in the time scales from few milliseconds up to few femtoseconds. Correspondingly, human or scientists and professors and technologists and they have developed the corresponding mimicked devices which work in the same time scales which are occurring in the natural thing. So lowest time scale which is available in nature is Bohr period of valence electron, which is 1 femtosecond. And correspondingly we have developed the lasers which can beat, which have the frequency of few femtoseconds. So to realize, जैसे मैंने seconds का पूछा था, how fast is femtosecond? Can somebody realize? बातें बाद में कर लेना यार, पहले सीख लो, ज्ञान बाद में नहीं मिलेगा. femtosecond में क्या क्या हो सकता है? And how fast is femtosecond? सेकेंड्स का तो बता दिया, मिली सेकेंड्स में भी बता दिया, माइक्रो सेकेंड में भी आप रियलाइज़ कर सकते हो. सो हाउ फास्ट इज अ फेम्टोसेकेंड? 10⁻⁻15 सेकेंड. सोच सकते हो कुछ? हाँ, लैटिस वाइब्रेशंस, ओके. बट फिजिकली अगर देखें तो सो इट टेक्स जस्ट 2.5 seconds if the light travels from earth to moon and come back. So now you realize how fast is femtosecond could be. So 2.5 seconds में तो light चांद से जाके वापस आ सकती है. And 1 femtosecond में आप कितना travel कर सकते हैं? 300 nanometers. If you ask you to travel 300 nanometers, you can cover it in just 1 femtosecond. So this is the realization of femtosecond time scale. So मैं जो काम करता हूँ, it's time resolved spectroscopy. आपने यूवी विजिबल स्पेक्ट्रोस्कोपी और फोटोल्यूमिनेसेंस स्पेक्ट्रोस्कोपी, लॉट ऑफ स्पेक्ट्रोस्कोपीज आर देयर एंड दे आर ऑल मोस्टली स्टेडी स्टेट स्पेक्ट्रोस्कोपी. वी वर्क ऑन द डायनेमिक्स पार्ट ऑफ दैट एंड वेयर द प्रोसेस स्टॉप्स. बिफोर दैट वी स्टडी ऑल द डायनेमिक्स, हाउ द प्रोसेस स्टॉप्स एंड हाउ द लाइट इंटरेक्ट्स विद द मटेरियल, and between the interaction and the completion of the process we study all those processes. So this is the basic of the time resolved spectroscopy. In 1872 there was a photographer named Edward Muybridge. He was asked to observe the जो घोड़े की चाल होती है, हॉर्स रेस होते हैं, उसको स्टडी करने के लिए उसको फंडिंग मिला. एंड somebody wanted to put money on the horse race. And what they said कि मुझे पता करना है कि घोड़ा कैसे दौड़ता है, तो so that I can put my most of the money on that particular horse who will travel fast. And travel fasting के लिए घोड़े को एक particular चाल चलना पड़ता है. So he took the snapshots, photographs लेता रहा. And what he did is that he combined all the photographs together and he generated that how the horse gallops, कैसे घोड़ा दौड़ता है. और जब घोड़े की चाल किसी को समझ में आ जाती तो जो शातिर बंदा होता है वो उसी के ऊपर ज़्यादा पैसा लगाता है एंड ही विंस. एंड ही कुड रिकॉर्ड एट दैट 1877 1 millisecond time resolution. And from there the concept of time resolved spectroscopy started. So in time resolved spectroscopy, in just few femtoseconds we take the snapshots of few femtoseconds, attosecond steps and then combine together and we can deliver that okay, this process is happening in this material. So we take the snapshots of various processes, combine them together and make the time resolved spectroscopy. And we need femtosecond lasers. So generally lasers, जैसे ये laser pointer है, this is a normal laser pointer. It is a CW laser, we call it CW laser. There are pulse laser which have a frequency, repetition rates. So one is CW laser and another is pulse laser. दो टाइप की lasers होती हैं. तो हम जो यूज़ करते हैं पल्स लेज़र यूज़ करते हैं. पल्स लेज़र की फ्रिक्वेंसी होती है 35 femtoseconds. In 35 femtoseconds we can study lot of phenomena which occur in natural processes. For example, there are certain transient states are available, there are induced states. So these concepts you may not be able to find in normal textbook or your own syllabus textbooks. Induced states I'll come later on one by one, and if you want you can discuss with me also later on. And then this intensity of this pulse laser is very high. It can damage the materials also. Unlike in UV or PL, it hardly damages your system, but this pulsed system they can damage also. Damage पे भी मैं आता हूँ. और एक आता है नॉन लीनियर फिनोमिना. लीनियर एंड नॉन लीनियर फिनोमिना में डिफरेंस क्या है? लीनियर फिनोमिना किसको कहेंगे? ओम्स लॉ पढ़ा है सबने? जोर से बोलो, पढ़ा है नहीं पढ़ा? क्या होता है? चलो V इक्वल टू आई आर मान लेते हैं. एंड उसमें कंडीशंस लगाई जाती हैं. क्या होती हैं? टेम्परेचर, प्रेशर एंड मॉर्फोलॉजी, वो सब जो है कांस्टेंट रहने चाहिए. बट अगर टेम्परेचर प्रेशर कांस्टेंट नहीं है तो क्या होगा? तो स्ट्रेट लाइन होगा वी आई आर का. क्या होगा? It can become exponential, it will not be linear. So Ohm's law is a linear phenomena, and non-linear is when it deviates from the linearity. So we study all these non-linear behaviors when we apply these femtosecond lasers, and non-linear phenomena generally dominates in many materials, because of which you can find out different properties can be achieved in different materials, which I'll show you one by one. So if we talk about absorption can happen in just 1 femtoseconds. In just 1 femtosecond, absorption can take place. Photon comes, it is absorbed by the electron. It can kick off the electron, or it can bring the electron to the lower states. There are electronic transitions which happens in nanoseconds time scale. Then there are internal conversion, vibrational relaxations, fluorescence, phosphorus. These are all part of the atomic physics. आप लोगों ने पता नहीं एटॉमिक फिजिक्स आपके कोर्स में भी है या नहीं है, बट दीज आर ऑल द कंसेप्ट्स विच आर अवेलेबल इन दिस atomic physics. And also we can generate terahertz radiation. Terahertz radiation is also a very for last 10-12 years or 15 years or so, it's a very important technique which is coming into the practical use. एक्सरे सबने पढ़ा है, एक्सरे सबने यूज़ भी किया होगा, कभी लड़ाई वड़ाई की हो तो हाथ पैर टूटे होंगे, तो एक्सरे करते आपको पता चल जाता है. देन देर आर माइक्रोवेव, सबने अपने घर में भी यूज़ करते होंगे. सो दिस टेराहर्ट्ज़ इज़ अ वेरी स्मॉल बैंड ऑफ रेडिएशंस विच कम्स बिटवीन माइक्रोवेव एंड एक्सरे रिजाइम. एक्सरेज को हम बोलते हैं कि ज़्यादा एक्सपोज नहीं करना चाहिए, बिकॉज इट कैन कॉज कैंसर्स एंड इट कैन आयनाइज योर बॉडी. But the beauty of this terahertz radiation is that it cannot ionize your human tissue, and it can give the exact one-to-one picture of your human tissue when it passes through that particular thing. एयरपोर्ट्स पे भी बहुत जगह आजकल लगे हैं, आप स्कैनर्स लगे, बॉडी स्कैनर्स हैं. किसी ने अगर अंदर कुछ भी छुपा रखा है बॉडी के अंदर भी, अगर किसी ने स्वेलो भी किया है तो पता चल जाता है. प्लास्टिक एक्सप्लोजिव्स आजकल बहुत कॉमन है, जिससे राजीव गांधी की डेथ हुई थी. वो केवल हम टेराहर्ट्ज़ रेडिएशंस के थ्रू ही डिटेक्ट कर पाते हैं, एक्सरेज भी इसमें डिटेक्ट नहीं कर पाते हैं. सो देर आर मैनी मल्टीपल थिंग्स, एंड नाउ डेज मोस्टली इंडस्ट्रीज प्रोडक्शन में इसको यूज़ करती हैं. दैट्स एंटायरली डिफरेंट टॉपिक. सो व्हाट वी डू, or what I did in NPL when I was in NPL, so we used short laser pulses to study ultrafast dynamics in physical systems, and we created non-equilibrium states. So everybody wants to be in the equilibrium state, rest position, lowest energy position. What we do is we disturb that equilibrium. जैसे मैं बीच बीच में क्वेश्चन पूछ रहा हूँ, आप लोग सो जाते हो तो मैं क्वेश्चन पूछता हूँ, you become excited. So we excite the systems by using these ultra fast lasers, and then when we get excited, only then I come to know कि भाई किसके कौन कितना बोल पा रहा है, किसके पास कितना knowledge है. Only then I can realize. If everybody is kept quiet, I may not be able to realize कि किसके पास कितना knowledge है. इंटरव्यू भी ऐसे ही होते हैं. हम क्वेश्चंस पूछते हैं, जब तक आप जवाब नहीं देते, अगर आप ऐसे ऐसे सिर हिलाएंगे तो हमें पता नहीं चलेगा. जब तक आप बोलेंगे नहीं, बताएंगे नहीं, तो दैट्स व्हाट द इक्विलिब्रियम स्टेट्स आर डिस्टर्ब्ड when we shine these ultra fast lasers or high intense lasers. And when we disturb the equilibrium, only then we realize the real property of that system is how stable that system is, how stable that compound is. For example, अभी शर्मा सर ने TiO2 का example दिया. So TiO2 is a very highly stable system, but it can be disintegrated. How TiO2 is formed, कैसे उसमें doping करना है, कितना doping करना है, all these things are known when you disturb the equilibrium states. And we can directly view the complete snapshot of the dynamics which are happening in the material when it forms. So TiO2 कैसे form होगा उसकी एक picture हम यहाँ से निकाल सकते हैं पूरा completely. And also we can use these ultra fast or ultra high intense pulse lasers for micro machining. माइक्रो मशीनिंग में क्या है, आजकल आपने स्टेंट्स देखे होंगे, जब हार्ट पेशेंट्स के अंदर स्टेंट्स लगते हैं तो दे आर ऑल माइक्रो मशीन्ड. एंड माइक्रो बहुत छोटा सा स्टेंट होता है, बट इट सेव्स अ लाइफ एंड इट इंक्रीजेज योर लाइफ फॉर 5 to 10 years. तो वो दैट माइक्रो मशीनिंग ऑफ दैट टाइटेनियम स्टेंट इज डन बाय यूजिंग फेम्टोसेकंड लेजर्स. एंड आजकल ऑपरेशंस आई सर्जरीज भी फेम्टोसेकंड लेजर्स से हो रही हैं. And we study a lot of photo excitation, microwave machining, and we can set up a lot of experiments by using just a single femtosecond laser. And important phenomena like FRET, PRET and MB effects. FRET is Foster resonance energy transfer. PRET is plasmon resonance energy transfer. ये आपके टेक्स्ट बुक में नहीं मिलेगा. एंड मॉस बस्टिंग इफेक्ट, ये बहुत इंपॉर्टेंट फिनोमिना है जब हम कोई भी मटेरियल प्रॉपर्टी यूज़ करते हैं. अब लेज़र्स पढ़ रखा है आपने कैसे काम करती है, पढ़ी है लेज़र, चलो ठीक है. तो लेज़र के लिए आपको एक सीड बीम चाहिए होती है. उससे सीड बीम से एक्साइट द इलेक्ट्रॉन्स एंड देन दे गो टू द कंडक्शन बैंड एंड देन व्हेन दे ट्राई टू कम बैक वो फिर लेजिंग करते हैं. सो सिमिलरली जब हमारे पास एक सीड बीम होती है तो हम क्या करते हैं कि इनिशियली हमारे पास एक लेज़र होती है, उसको हम स्ट्रेच करते हैं. फॉर एग्जांपल यहाँ पर 800 नैनोमीटर 400 मिलीवॉट की लेज़र है और 35 फेम्टोसेकंड्स इसकी पल्स विड्थ है. इसको हम स्ट्रेच करते हैं इन टाइम रिजाइम. सो 35 फेम्टोसेकंड से हम इसको नैनो सेकंड्स तक या पिको सेकंड्स तक लेकर आते हैं, उसका टाइम बढ़ा देते हैं. एंड देन वी एम्पलीफाई इट. एम्पलीफाई कैसे करते हैं, जब हम लेज़र को किसी भी मीडियम से, नॉन लीनियर मीडियम से पास थ्रू करेंगे मल्टीपल टाइम्स, तो मल्टीपल रिफ्लेक्शन से उसकी इंटेंसिटी बढ़ जाएगी. वेरी कॉम्प्लिकेटेड फिनोमिना बट वी रियलाइज इन द लैब. एंड देन वी कंप्रेस the time from few nanoseconds or picoseconds to again 35 femtoseconds. So and we get an amplified high intense 800 nanometer femtosecond laser which beats in 35 femtoseconds time scale. And जो इसकी पावर है ये जस्ट कुछ मिलीवॉट पावर है. it may not damage your tissues, but this femtosecond laser is so powerful that it generates petawatt power, 10 to the power 15 watt. So in just few seconds it can burn and it can drill the hole inside your hand also. If it is like shine for longer time, it can burn anything. और आजकल जो वॉरफेयर में फेम्टोसेकंड लेजर्स का काफ़ी यूज़ होने जा रहा है. अभी नेक्स्ट जो वॉर होगी उसमें आप देखेंगे केवल लेज़र से लड़ाई होगी. So these are some of the systems that we have developed in our lab. So some of the systems are purchased and some of the systems are established by using the existing optics. So this is the system where I work on. This is the transit absorption system. In this one, what we do is we have a beam. Coherency पता है? Coherent, what is coherent light? Same phase. So एक लेज़र को हम स्प्लिट करते हैं दो पार्ट में. उसका एक पार्ट को हम यूज़ करते हैं एज ए पंप, एक पार्ट को हम यूज़ करते हैं प्रोब. Pump is a highly intense or highly energetic beam and probe की intensity थोड़ी सी कम होती है but it is wide. Pump में क्या होता है, सिंगल फ्रिक्वेंसी मोनोक्रोमेटिक बीम होती है. फॉर एग्जांपल इट, एंड हाउ डू वी चूज इट, वी चूज इट डिपेंडिंग ऑन द बैंड गैप ऑफ द मटेरियल. सो जितना कम बैंड गैप होगा उतनी हम IR रेंज में जाएंगे, अगर ज़्यादा बैंड गैप होगा तो हम UV रेंज में जाएंगे. So we can select the monochromatic beam based on the band gap of the material. And the probe beam, it's a white light continuum. It has all the wavelengths from say 350 nanometers up to 1600 nanometers. And we call it white light continuum. It's not a white light, but it's a continuum of various frequencies, and it used as a probe. When the two beams they fall on the sample, the pump beam excites the electrons from the वैलेंस बैंड. जब वैलेंस बैंड से इलेक्ट्रॉन्स जाएंगे तो कहाँ जाएंगे? कंडक्शन बैंड में जाएंगे. तो जब कंडक्शन बैंड में जाएंगे उसके बाद हम प्रोब बीम भेजते हैं, एंड देन प्रोब बीम सीज कि कितने इलेक्ट्रॉन्स वैलेंस बैंड में पहले थे, एंड आफ्टर सर्टेन टाइम हाउ मेनी इलेक्ट्रॉन्स आर लेफ्ट ओवर इन द वैलेंस बैंड, एंड नाउ हाउ मेनी इलेक्ट्रॉन्स आर सिटिंग इन द कंडक्शन बैंड. So this is a very important phenomena for realizing various properties of the materials. So this is how we perform this spectroscopy. And then as I said that non-linearity multiple types की होती हैं, और उसमें I'll not go into the hi-fi things, but जब हम deviation देखते हैं एक linear property से non-linear property में, sometimes cloaking effect आपने पढ़ा सुना है? Cloaking effect, बंदा गायब हो जाएगा. So this is how we can realize through this Z-scan. So this is Z-scan where we move we collimate and focus the beam on a very small point, and then we move the lens, and when the lens is moved the beam is defocused again, and we measure the scattered or reflected light on the detector. There we can realize two type of phenomena. One is where the refractive index is more than 0, and where negative refractive index can also be observed. Negative refractive index पढ़ रखा है आपने? नहीं पढ़ा होगा. I'll come to that. And then we can do the laser induced breakdown spectroscopy. This LIFS technique is used in various moon missions or Mars missions, where a small device can probe what is present in the crest of any terrestrial body. जो मून मिशन पे डिवाइसेस गया था, मार्स मिशन पे गया है, वहाँ पर इस तरह के छोटे छोटे डिवाइसेस भेजे गए हैं जो लिप्स से उसको एक्सट्रैक्ट करते हैं प्रॉपर्टीज़ को. इट्स काइंड ऑफ एटॉमिक एब्जॉर्प्शन स्पेक्ट्रोस्कोपी, बट इट इज़ अ वेरी यूजफुल प्रॉपर्टी. देन हाई हार्मोनिक जनरेशन, एंड then direct laser writing. Direct laser writing say you can create whatever structures you want on the substrate. And this is the lab in which I am still working. And जो typical signal होता है transient absorption spectroscopy और femtosecond laser spectroscopy का, it looks like this. So केवल तीन ही फीचर होते हैं, एक पीक, दूसरी पीक और ये तीसरी पीक. इन तीन पीक से हम पूरा स्नैपशॉट बता सकते हैं. तो फर्स्ट पीक बताती है ग्राउंड स्टेट ब्लीच. तो ग्राउंड स्टेट ब्लीच क्या होता है? जब हमने एक्साइट किया किसी भी मटेरियल को, तो इलेक्ट्रॉन्स जो हैं ग्राउंड स्टेट से एक्साइटेड स्टेट्स में जाते हैं. तो हाउ मच इलेक्ट्रॉन्स हैव कम आउट ऑफ ग्राउंड स्टेट वी कैन टेल थ्रू दिस फीचर. अनदर फीचर इज स्टिमुलेटेड एमिशन, व्हिच इज आल्सो वर्कड इन लेजर्स आल्सो. तो जब इलेक्ट्रॉन्स कंडक्शन बैंड में जाते हैं एंड द क्वांटिटी ऑफ इलेक्ट्रॉन्स बिकम हायर इन दैट पर्टिकुलर स्टेट, द रेस्ट ऑफ द इलेक्ट्रॉन्स आर पुश्ड बैक टू द ग्राउंड स्टेट. This is called stimulated emission. We can study how many electrons, how much electrons, and at how much time they are stimulated back to the ground state. And another phenomenon is absorption. This is kind of steady state absorption, but we call it photoinduced absorption, because the probe beam जब वहाँ पे conduction band electrons में excited electronic states पढ़ रखी हैं आपने? ठीक, I'll come to that. So first excited state electronic state से second electronic state में electrons जाएंगे. Probe beam gets absorbed in that second electronic state, और वहाँ से फिर वो आगे jump करके next electronic state में जाएगी. This is called the photo-induced absorption. And we measure this all this phenomena with certain delay from few femtoseconds up to few nanoseconds. तो few femtoseconds से लेकर few nanoseconds और some few up to few nanoseconds तक जो भी phenomena उस material में हो रहे हैं, during the formation and after the formation, we can study this with the help of this. So this is the typical setup of control spectroscopy. And this is a very famous diagram. कोई पहचान सकता है इसको? ये वाला, लेफ्ट वाला पढ़ रखा है, देखा है कहीं? ये टॉक नहीं है, तुम्हारा टेस्ट भी है. दिस इज कॉल्ड जेब्लॉन्स्की डायग्राम. जेब्लॉन्स्की डायग्राम आपको क्या बताता है? अगर आपने एटॉमिक फिजिक्स थोड़ी बहुत पढ़ी होगी, तो एवरी मटेरियल हैज इलेक्ट्रॉनिक स्टेट्स, वाइब्रेशनल स्टेट्स एंड रोटेशनल स्टेट्स. So all electronic states are composed of vibrational states and vibrational states have rotational states. Rotational states को हम Raman spectroscopy के थ्रू चेक कर सकते हैं. वाइब्रेशनल स्टेट्स के को हम there are different vibration spectroscopy. Certain electronic states को भी हम steady state electronic states को study कर सकते हैं. But the dynamics of these electronic states and vibrational states can be studied by using this femtosecond spectroscopy. So what happens is that as soon as the light comes, it excites the electrons to 5 minutes. So it excites the electrons to higher states and then they slowly relax to the ground states. So there are certain systems. One is called system crossing and then internal conversion. A lot of phenomena happen, and we realize all these phenomena in the material during the formation of the material. And this is how the white light probe or the continuum is formed using this femtosecond laser. So this is a detailed Jablonski diagram, and this is another Z-scan that I was telling that. Yes. I said that cloaking effect. So when there is a high intensity beam is applied on a material, if the absorption increases with the intensity, then materials become opaque. But if the materials become at certain high intensity, materials can also become transparent. So you can, the beam or the radiation can pass through that material also. So this is called the non-linear Z-scan, where we can study the negative refractive index also. As I told you that femtosecond laser intensities lasers are very intense and it can damage the system. If we compare two lasers, one is nanosecond lasers and another is femtosecond lasers, what you can see that femtosecond lasers can swiftly or softly drills a hole. It does not damage the system. This is femtosecond lasers. And when we apply the nanosecond lasers or the short duration lasers, higher duration lasers, it damages the complete system. So it is easy to work with femtosecond lasers than nanosecond lasers, because somebody can say that if the material can be damaged, then how can we study this, use these femtosecond lasers? So this is the beauty of femtosecond laser. It does not affect. So if there is a film on the surface, you can see by using the nanosecond lasers, it has ruptured and created the melt zone and other things. But femtosecond lasers can probe from the substrate, from the top of the substrate film to the bottom of the substrate also. And this is again the effect of femtosecond lasers and nanosecond lasers. So femtosecond lasers, say we can create lot of different materials. So as I told you that stents are made of these femtosecond lasers. And this is one of the system that we have studied in our lab. It is on silicon surface. Silicon is a very beautiful material, and still for last 50 years people are studying, and a lot of things are to be explored in silicon. One good thing I would like to say that silicon is a semiconductor, okay, but you can make it metallic. You can make it metallic just by heating it. By heating it, it can rearrange the metals on atoms on the top of the surface, and the top of the surface can become metallic. So that is called silicon 111 and here we can study the as yesterday also there was mentioned that we can create metamaterials, and metamaterials have the properties that they can absorb the lasers, and they can reflect the lasers, and then they have wonderful properties. You can tune the properties of different substrates, where you can you can enhance the properties multiple times by creating these metamaterials. We we can create the surface plasmon resonance, and surface plasmon resonance are used widely used in biological sites when you are creating these biomedical sensors and biomedical devices. So especially for biomedical sensors, the surface plasmon resonance are used. आजकल जो kits आती हैं उसमें SPR phenomena ही use होता है, जहाँ पर आप छोटा सा एक drop of any sample you put and then it gives the signal of what is present in your blood or whatever sample you are using. I'll stop here. This is topological materials. As I told you that this is divided into two parts, and so now my actual experiment starts. So we have studied a lot of topological materials. We have studied the formation of terahertz radiation, different phenomena. We have devised, we have formulated different effects. So important one, just one last important concept is mass bursting effect. Conduction band, valence band सबको पता है, Fermi level सबको पता है. There are certain phenomena that when you excite the electrons to higher states, a band gap is there and you can tune the band gap. So by creating this mass bursting effect or by using this mass bursting effect, you can tune the band gap of the material. What we did in this experiment, and there are again 2D materials and other things. So this is all, and these are all my collaborators and friends and students who have contributed to this research. Thanks.
Thank you, sir, for your nice presentation and nice work. Now session is open for question and answer. Yeah.
I think I had a bit of a misconception. So you showed your ultra-fast lasers. How do we make these ultra-fast lasers? So because you said as we increase intensity, the damage increases. I was under the impression that when we make a femto laser, we're increasing the intensity because we're squishing the laser to a higher peak. So what is it exactly that is splitting when you're converting a low frequency laser to a high frequency laser?
So there are non-linear materials. Generally, we have a titanium sapphire crystal, which produces this femtosecond lasers at 800 nanometer. And there are a lot of other phenomena, like for example, some frequency generation, different frequency generation. By using that, we can generate different frequencies, and also there are multiple optics where we can. So we use gratings to disperse the beams in time scales, and in so that and we can use the same gratings to reduce the time scales to femtoseconds. So grating is one of the important aspect in this femtosecond lasers.
Okay, so as you decrease the time scale, the intensity doesn't really...
Intensity varies. So if we reduce the time scale, then intensity also reduces.
Oh, it reduces?
Yes,
okay.
It reduces. Intensity increases when we do the multiple passing of the these lasers through the nonlinear medium. So multiple passing, there are two mirrors which are dichroic mirrors. They are called dichroic mirrors, and when they pass, multiple passes are there, the intensity increases.
Thank you.
Okay. Sorry, we have very limited time. So please proceed.
I request our esteemed chairperson, Professor Jai Singh, to kindly felicitate Dr. Mahesh Kumar Sharma by presenting him a planted pot. A memento. And a certificate. Please give a round of applause.
During the session 4, we have two oral talk. First talk will be Miss Anju. Yeah, please. She is from Netaji Subhash and University, Technical, Delhi. You have 7 minutes, madam. Okay. Only 7 minutes.
Okay. Good morning, everyone. My name is Anju. I am from Shivaji University of Technology, and I am here to present my research work on exploring the electrochemical performance of nickel sulfide for supercapacitor applications. Next. And this is the outline of my research work: synthesis and the characterization XRD, UV, and FSM ADX, and further the electrochemical investigation for supercapacitor analysis, and then conclusion. This is a brief discussion about nickel sulfide, and this is used for supercapacitor batteries, electrocatalyst, photocatalyst, sensors, etc. And this is a synthesis which I have used hydrothermal reaction, and in hydrothermal there are two or more precursors, and here I am using nickel sulfide, nickel nitrate hexahydrate plus thiourea, and after the 1 hour stirring I transferred this in Teflon cup, then stainless steel autoclave, then allowed to have hydrothermal reaction 200 degrees centigrade for 18 hours, then cooled down it and collected the precipitate and washed it and centrifuged it, then dried it in a vacuum for overnight and collected the nickel sulfide powder. This is the X-ray diffraction and UV visible spectroscopy, and in X-ray diffraction spectra Ni3S2 and NIS, there are mixed phase in this XRD spectra, and UV visible spectra there is band gap is 1.1 electron volt. This is the FSM and ADX morphology analysis. I get the irregular shape of FSM image. This is the electrochemical analysis in GCD. There is potential range from minus 0.6 to plus 0.45. This is the 1.05 potential range with current density 12, 10, 8, 6, 4 ampere per gram, and this is the CV cyclic voltammeter in scanned 100, 80, 60, 40, 20 and 10 millivolt per second. I got the specific capacitance 2992, approximate 3000 farad per gram, and this is the specific capacitance increases with current density increases, and this is the Nyquist plot here showing the calculated and fitted and the equivalent circuit. This is the conclusion, and this is my presentation. Thank you so much.
Thank you within time, and now session is open for your question.
ये यूवी कैल्कुलेशन हमारे एनएसयूटी में है,
आपने खुद किया है?
आपने खुद हैंडल किए हैं?
यूवी एंड सीवी इलेक्ट्रिकल को मैंने खुद हैंडल किया। हाँ जी, एंड एक्सआरडी एंड एफिसम मिक्स से कराया है।
एक्सआरडी की पीक है, इससे क्या समझते हो?
सर ये दो मिक्स फेस हो रहे हैं,
बहुत सारी पीक आ रही है ना उसी चीज़ में।
हाँ जी
सर, जो स्पेक्ट्रम है पैटर्न है।
साड़ी नहीं होगा, नीचे नीचे लो लो।
सर उसमें ब्लैक एंड रेड दो पिक्स, दो तरह की पिक्स दिखाई गई हैं। जो Ni3S2 है वो ब्लैक में।
एक्सेल की पीक है,
इससे क्या समझते
मैं
हो?
क्या समझते हो? इंटेंसिटी है लिख रखा है लेफ्ट साइड में आपने।
सर ये 2 थीटा डिग्री और इंटेंसिटी के बीच स्पेक्ट्रा है हमारा।
इससे क्या समझ में आया आपको? पीक जो बढ़ रही है, जो छोटी जो बड़ी है,
इंटेंसिटी
इसकी
उसमें क्रिस्टलाइन फेस होता है। अगर हम
इंटेंसिटी किन किन बातों पे डिपेंड करती है?
इंटेंसिटी एक तो फेस पे और क्रिस्टलाइन स्ट्रक्चर पे। अगर हमारी ब्रॉड पीक होगी ज़्यादा तो अमोरस स्ट्रक्चर होगा, इरेगुलर शेप होगा। तो अगर फाइन ज़्यादा इंटेंसिटी पीक आती है तो वो क्रिस्टलाइन स्ट्रक्चर होता है उसका।
और एमॉर्फस कैसा होगा?
अमोरफस उसकी बहुत ज़्यादा बड़ी पीक होगी और इतनी फाइन नहीं होगी, मतलब ऐसे जा रही होगी, बहुत बड़ी सी ब्रॉड होगा
अच्छा,
स्ट्रक्चर।
ये स्पेक्ट्रम है, पैटर्न है?
सर एक्चुअली हमने अमोरफस कराया
नहीं सर, बेसिक वो क्वेश्चन पूछ रहे हैं बेटा, ये स्पेक्ट्रा है या पैटर्न है, ये है क्या?
स्पेक्ट्रा।
हाँ नहीं यही तो तैयारी करनी, यही तो
EU का मतलब क्या होता है?
आर्बिट्रेरी यूनिट।
मतलब क्यों डालते हैं EU?
आपने दोनों डाला हुआ है, इसमें टिक भी है, इसकी वैल्यू भी है, इसमें इंटेंसिटी वैल्यू भी है, इसमें दे रखी है आपने।
कोई पढ़ लेना, क्यों डालते हैं? कभी इंटरव्यू में पूछ सकते हैं। दूसरा, टॉप प्लॉट कैसे प्लॉट किया आपने?
तो प्लॉट वो फॉर्मूला होता है उसका।
टेंजेंट मारी है
हाँ
कैसे?
जी, टेंजेंट किया है वो। सर वो जीरो पे जहाँ तक पीक खत्म होती है ना, जीरो पे, तो जीरो पे हम उसमें देखते हैं कि
थोड़ा सा टिल्ट कर दूंगा, बैठ कर चेंज रहेगा।
हाँ जी, वो टेंजेंट।
टेंजेंट कैसे ड्रॉ करिए?
कैसे एक्यूरेसी कैसे पता चले कि आपका जो प्लॉट किया
सर
परफेक्ट है?
ये जहाँ पे कितना इंटरसेप्ट कर रहा है ना, यहाँ से।
नहीं तो अगर मैं थोड़ा सा टिल्ट कर दूंगा तो मेरे को बैठ
सर
जाएगा।
वो पर दिखेगा नहीं ना, वो टेंजेंट से नहीं आएगा ना फिर।
मतलब टेंजेंट सही से कैसे कैसे डालिए? स्केल डाल के या
यहाँ
कैसे?
पे, यहाँ इसको मैच किया है। कोई पीक होती है ना तो ऐसे टेंजेंट जा रहा होता है, तो उसको
इंटरसेप्ट
मैच
भी होता है,
करते हैं।
इंटरसेप्ट
क्या
इंटरसेप्ट होता है।
इंटरसेप्ट होता है सर?
ये थोड़ा सा वेरिएशन करते हैं ना, 0.2 0.3 का गैप वेरिएशन तो वैसे ही आ जाएगा बैठ जाएगा। तो इसको बहुत ध्यान से करना होता है, ऐसे नहीं कि टेंजेंट ड्रॉ कर दी वहीं पर मार दिया। थोड़ा सा पढ़ लेना। अच्छा किया है वैसे, बट
नहीं सही किया हुआ है सर, पर टेंजेंट इतना ही आएगा उसका।
नहीं सर ही okay, good, take it. Second oral presentation by the
Thank you so
Kanika
much.
and C for Rental Institute Indore. Please. Only 7 minutes.
Good morning everyone. I am Kanika Maheshwari. Right now I am pursuing my PhD from Oriental University Indore. First of all, I would like to thank all the organizers, especially Dr. Surendra Kumar, to providing me the opportunity to present here. So today I am presenting with the topic salt engineered pectin PVA biopolymer electrolytes, sodium azide driven structural analysis and ion transport pathways for green solid electrolytes. Next. As in the morning session, Dr. Sanjeev Sharma has already emphasized enough for the necessity and requirement for the environmental friendly or sustainable solutions for the world. So in the same thing for the energy storage devices, we want environment friendly solutions. So right now we all know that we are using lithium ion batteries, right? We are using lithium ion batteries and we all know that lithium ion is toxic in nature, right? So we want some environmental friendly solutions. And even when we are talking about the electrolytes, so traditional liquid electrolytes, they offer a very good conductivity of almost 10 to the power minus 3 to 10 to the power minus 1 Siemens per centimeter. But still there are some limitations of them. That is that they are leakage, can be leakage and there is limited thermal stability. So what we are doing, we are switching to solid polymer electrolytes. And when we are switching to solid polymer electrolytes, the researchers have done immense work on the synthetic polymers. But still, when we are talking about synthetic polymers, they are also, non-biodegradable. So what we are doing, we are switching to biopolymers because, they are sustainable, they are biodegradable. So these are some kind of bio-based polymers. So what I am using in the material, that is pectin. So pectin is a polysaccharide, and we can found pectin in the plant cell walls, wall cells, and even it's the peel of the fruits like citrus fruits and guava peel. We can find the pectin material. The main interesting thing is that pectin have hydroxyl and carboxyl group, which we can tune with the for the conductivity purposes. And the other polymer I am using, that is PVA. So this is my research methodology. I have used solution casting method to prepare polymer electrolyte films. We have taken pectin and PVA in 50-50 and 80-20 ratios, and then we have used distilled water as a solvent. So first we stirred pectin and PVA at 70-80 degrees centigrade for 2 hours, and then we added sodium azine in different concentrations. And after that, when we found the viscous solution, we poured it into a petri dish, and we kept it at room temperature for drying for almost 24 to 48 hours. Then we got these flexible, almost transparent electrolyte films. The characterization which I am presenting today is FTIR in electrochemical impedance spectroscopy. So basically in electrochemical impedance spectroscopy, generally we plot Z dash and Z double dash as Nyquist plot or Kolkol plot. And when we found the bulk resistance from there, so we all know the conductivity formula, right? Then we use it and calculate the conductivity. So this is my FTIR analysis. As you can see in the this is pectin PVA in 50-50 ratio and pectin PVA in 80-20 ratio. So we can see that this is the OH stretching part. So basically there is a good OH stretching vibration. That means pectin and PVA are working, well with each other. They are having hydrogen bond. So here we are finding the peak for hydroxyl group, and here we are finding peak for the CH group. In the similar manner, when we doped sodium azide in both the ratios 80-20 and 50-50, actually we found a peak at almost 2100 to 2130 centimeter inverse. So it peaked, and that represents actually azide group. So that means that sodium azide is well dispersed in our polymer electrolyte. So this is electrochemical analysis. So for 80-20, I got maximum conductivity for 1% sodium azide dispersion, and for 357 I almost got a plateau. There is no increment in the conductivity part, and for 10% then there is a slight increment. For 50-50 ratio, I got highest conductivity for 7%. So these are the graphs for dielectric constant and dielectric losses and electric modulus for 80-20 composition. And as we all know that as frequency increases, dielectric constant decreases. So the results are well versed in the. These are the results for 50-50 pectin PVA ratio. This is the conclusion. We got 8.15 10 to the power minus 4 Siemens per meter for 1% azide doped 80-20 ratio, and maximum for 50-50 we got 3.20 into 10 to the power minus 4 Siemens per meter for 7% azide doping. So as we already see that for the 80-20 conductivity, there is a maximum conductivity at 1%, and after that there is a plateau, and there is slight increase at the 10% ratio. So I wanted to further prepare that what happen when we are doping 15%, 20% sodium azide. But the issue I am facing that films are not getting dried, or if they are getting dried, they are getting cracked actually. So there is some things we need to tune and understand how we can go further for this. So I want to really acknowledge Professor Bhaskar Bhattacharya, Mahila Mahavidyalaya BHU, for giving me the opportunity and for providing continuous guidance and support for my research work.
Okay.
Thank you.
Thank you. Now, open for a question.
You've shown conductivity data.
Yeah, okay.
You've shown conductivity data, but Um, I'm not entirely sure, do you care about just in plane conductivity? Do you also care about through plane conductivity? Have you done those two measurements? Are you just putting electrodes on the side of the film, or are you putting it across on both sides?
No, on the sides of the films, and we are doing the plane conductivity.
All right.
How do you optimize the steering temperature and steering time?
Steering temperature and steering time. Actually सर hit and trial था because जब हम पैक्टिन की बात करते हैं तो पैक्टिन जो है वो बिलो 60 पे से पहले जो है डिज़ोल्व होता ही नहीं है वाटर में. सो और पीवीए जो है वो ऑलमोस्ट 80 पे जाके ही डिज़ोल्व हो पाता है. तो थोड़ा हिट एंड ट्रायल किया था और उसके बाद में आई ऑप्टिमाइज कि अगर अराउंड 70 to 80 टेम्परेचर रखेंगे तो पैक्टिन और पीवीए जो है वो दोनों डिज़ोल्व हो जाते हैं. एंड देयर इज़ ए गुड क्रॉस लिंकिंग बिटवीन दैम.
रेफरेंस नहीं पढ़ा आपने?
यस सर, रेफरेंस की बेसिस पे भी मतलब जो टेम्परेचर मुझे मिला वो अराउंड 80 ही था पीवीए का भी.
एफटीआर से क्या मेजर करते हैं?
सर एफटीआईआर से बेसिकली वाइब्रेशंस दिख रहे हैं हम. तो जैसे
हमारा ऑब्जेक्टिव क्या है उसको?
सर हमारा ऑब्जेक्टिव ये है कि अगर हम सोल्ट डोप कर रहे हैं लेट से, तो जो सोल्ट है उसका जो आयन है वहाँ पे इंटरेक्शन हो रहा है या नहीं हो रहा है, दैट इज़ वेल डिस्पर्स्ड इन आवर पॉलीमर मैट्रिक्स और नोट. अगर लेट से अगर मेरे पास में मेरा OH ग्रुप है वहाँ पे अगर मेरे पास पीक में कोई शिफ्ट नहीं हो रहा है, दैट मीन्स जो सोडियम आयन मैं डाल रही हूँ.
जैसे यूवी यूज किया आपने बैंड गैप निकालने के लिए,
एफटीआईआर यूज़ किया सर मैंने
एफटीआर क्या निकालने के लिए किया?
कि if my sodium azide salt in well dispersed in the polymer matrix or not. So मैंने FTIR यूज़ किया वो पता करने के लिए.
Okay, thank you.
Thank you so much.
I would like to thanks to our invited speaker and oral presenter. Okay, right now I am doing.
We will now take a short tea break. Kindly resemble here as we resume the session in 5-10 minutes. Tea will be served at the Samarth brew around the auditorium.
लास्ट टॉक भी थी
कब
उनकी।
बेनिफिकेशन कब चेयर सेशन वही तो है सेम सेम ही है अब वो जो स्टार्टिंग में बस उनका ध्यान से नीचे
हाँ जी, हाँ जी। और 110 में कितने में? उसमें से थोड़ा सा बॉल मध्य प्रदेश। एक्चुअली मम्मा मेरी दिल्ली से है, तो मतलब उनकी तो शादी गोलन में थी, तो नानी बहुत सारे फैमिली होते हैं, और बुआ की शादी भी दिल्ली हो गई थी, तो वो यहाँ पर रहती थी दिल्ली में। तो समर वेकेशन सारी गर्मी की छुट्टियाँ। हाँ जी, करोली वाली माता जो ओके, बोले हाँ जी। नहीं, मेरी फैमिली मतलब हमारी एक्चुअली फैमिली जो है वो मुल्तान से, मुल्तान से पहले पार्टी पता है मुझे बहुत सारे लोगों ने बोला है, मेरे बहुत सारे दोस्त बोलते हैं कि ये ऋषि सुनक जैसी शक्ल है। मेरे कुछ दोस्त हैं, उन्होंने वो फोटोशॉप से क्या किया, ऋषि सुनक की फोटो लेके उसमें उसकी शक्ल लगा के मेरी शक्ल लगा दी।
जो बोलने का स्टाइल है
मैकमास्टर यूनिवर्सिटी नहीं, कनाडा। मैकमास्टर यूनिवर्सिटी, अभी आपको मैं तो दिखाऊंगा, मैं न्यूट्रॉन्स का काम करता हूँ। तो कनाडा में सिर्फ मैकमास्टर यूनिवर्सिटी में है, और वो शुरू हो रही है एक्चुअली कनाडा में हुआ करती है। हाँ जी, मैकमास्टर में। तो बहुत सारी अलग अलग टाइप की होती है, मतलब जैसे अभी तक मैंने सिर्फ यूज किया मैंने अभी जैसे हम क्या कहते हैं अपने मटेरियल्स बनाते हैं, अपने मटेरियल को हमें कैरेक्टराइज करने के लिए जो भी जिस भी टाइप की टेक्निक चाहिए, जैसे न्यूट्रॉन डिफ्रैक्शन, बिल्कुल, तो हम जैसे पाउडर न्यूट्रॉन डिफ्रैक्शन हम करते हैं, हमारे पास सिंगल क्रिस्टल्स वाले जब होते हैं हम सिंगल क्रिस्टल न्यूट्रॉन डिफ्रैक्शन करते हैं। अभी इसमें है ओके। तो आपको सर मैं कर रहा हूँ ओकरिज नेशनल, हमारे हम ओकरिज में करते हैं, टेनेसी में, यूएस में। हाँ जी, और वो बिल्कुल फ्री ऑफ कॉस्ट, फ्री ऑफ कॉस्ट। आ जाओ आ जाओ। I've already given.
Welcome back everyone. I hope all had a refreshing break. We now resume the conference proceeding with session 4. With this, I now respectfully hand over the proceeding to you, ma'am.
Okay, so on the behalf of Professor Jaisingh sir, I would chair this session. So now I would call Mr. Rachit Kapoor from Brock University, Canada. So he will deliver his talk from disorder to dimness.
I'll put it on my caller. Can I have the presentation switcher, please? Thank you. All right. All right. Good morning, everybody. I'm Rachit. This is my work from disorder to dimers, and I'll be talking about a material, bismuth terbium germanate. This is a material that I hope by the end of this presentation you would understand, hopefully, a little bit about it. The presentation has been made in the sense where everybody can have an introduction and understand what it's about. So, I work with magnets, and we've all had childhood memories with magnets. We've grown up playing with magnets. We've wondered what happens. We grow up, we learn in school that, magnets, unlike poles, attract and like poles repel. We grow a bit older, and then we realize when we study physics that magnetism is just motion of charged particles. So every atom is inherently magnetic. Now, this magnetism of atoms don't exist in isolation. So, for example, we can have atoms that talk to one another in a ferromagnetic interaction, where nearby atoms would tend to align their spins in the same direction, and we get a ferromagnetic material. We can also have something else, where neighboring atoms tend to align themselves opposite to each other, cancelling out their spins, resulting in something known as an antiferromagnetic material. Now, something really interesting happens when we introduce entanglement to the idea of antiferromagnetism. So let's assume these two spins. These two spins are antiferromagnetically ordered. So what's happening is
So what's happening is these two spins are entangled, which means these spins are fluctuating. Now the way they fluctuate is, these spins don't stay still. They're always changing their position and they're in a constant superposition of one another. But at every given instant, they're always opposite to each other. This is also known as a singlet state. It is given by the wave function 1 over root 2, up, down, minus, down, up, which are the two possible configurations. This is a total spin of 0 and also a total Sz, or the magnetic component of 0. A singlet state can be excited in 3 ways, which gives its name a triplet state. Now, let's say these two spins, they can either, one of them can excite and they can become up, up. You can excite them and become up, down. You can also excite them and become down, down. These have the magnetization of +1, 0, and -1. Now, before I move any forward, we've got to ask ourselves a question: why should you care about what I'm talking about? I'm talking about quantum diamomagnets, and today in this world, all countries are really racing towards building quantum computers. It's a very important technology, and it's a matter of national security for many countries. Now, quantum computers have to be benchmarked, and quantum diamomagnets are the simplest version of a quantum magnet. So they're oftentimes used to benchmark the performance of quantum computers. Which brings me to the hero of my story, which is bismuth ytterbium germanate. It's a material that I've been working on. If you remove the noise from this crystal structure, you see that it has ytterbium ions that are magnetic. And each ytterbium ion has one unpaired electron, which makes it sort of behave like just an electron. So it behaves like a spin 1/2 particle that I've been showing it to you all this time. In 2023, a research group in India, Mohanty et al., they found that this material, the nearest ytterbium atoms, form entangled dimers, just the same dimers that we saw earlier. The question is, how do we know about these dimers? They perform susceptibility versus temperature, and they basically fit the plot of susceptibility versus temperature to the predicted theoretical value for a quantum diamomagnet. They in fact claim that this simulation results in the fitting of an isolated spin dimer. We'll talk about what these are in a minute. But the question is, how can I directly probe this? This is fitting. I'm fitting some data of susceptibility versus temperature. There are many models and many fittings that are possible. The way to directly probe this is neutrons. The neutrons, we know, they've got no electric charge, but at the same time, because of their internal quark structure, they have a magnetic moment. So we use these to probe magnetic properties of many different materials. Now my research supervisor and I were wondering, we were looking at this paper, and we said, now in this material, bismuth and ytterbium, they've got very similar ionic radii. They've got identical valence states, they've got the same symmetry constraints in this crystal. The difference is bismuth is non-magnetic. We asked the question, what if this material had site mixing? What if bismuth and ytterbium are not really in their independent site locations but mixing together? In fact, Mohanty et al. Did their research studies but didn't claim to see any site mixing. The reason behind that is possible, which is bismuth and ytterbium have very similar X-ray cross sections with a relative difference of only 31%. So laboratory X-ray might not be able to pinpoint that. Whereas on the other hand, neutron cross sections have a total relative difference of 108% between the same two atoms. So that's what we did. We made these samples and I sent them off to Oak Ridge National Laboratory in Tennessee, USA, and we shipped it off to Daniel Laney, an instrument scientist over there, and we performed our powder neutron diffractions, which is very similar to X-ray diffraction, but we use neutrons instead of X-rays. Now we see this pattern. Now what's interesting is this pattern was taken at 20 Kelvin. Now if I cool this pattern down and I take the same neutron diffraction pattern at 50 millikelvin, which is what the machine can go to, we still find no differences. These two plots are exactly the same. There's no magnetic peaks down to 50 millikelvin. That means this material shows no magnetic ordering. What's more, we were actually totally correct in our assumption. This material has huge site mixing. So roughly 20% of bismuth atoms are literally eating the ytterbium atoms out of their sites. They're kicking them out. Now, if you remember, bismuth is non-magnetic. It is incapable of making these quantum dimers. So this material now has broken dimers. It has massive structural disorder because of the side mixing of bismuth. Now, we still wanted to answer, what about the claim of isolated dimers? What do they mean? This means that these dimers that we saw earlier are not interacting within each other. So this dimer over here is totally unaware of the presence of the dimer present over here. To test that claim, we again look forward to neutrons and we look at an elastic neutron scattering. Now in elastic neutron scattering, a neutron enters a material and excites it. When it does that, we find some energy transfer. We send a neutron with a specific initial momentum, and then we also obtain the final momentum that it's come out with. We calculate that difference, which is known as Q, which is also defined as momentum space. And we make a plot by sending different neutrons of different Q transfers and measuring the energy transfer. And we make a spectroscopic plot between the energy transfer and the momentum transfer. So it gives us sort of an idea of what is happening to the excitations of the material. Upon doing this, we send this over again to Oak Ridge National Laboratory, to hybrid spectrometer, high spec. Dr. Vasil Ogalia performed our experiment and we saw exactly what we expected. So this is a triplet excitation that you can see over here. These are the elastic peaks that we saw earlier in the neutron diffraction pattern, and this is the excitation. This is the triplet excitation in bismuth ytterbium germanate. Now something interesting to see is, on the left hand side of this plot is another quantum diamond magnet. This is ytterbium silicate. The only difference between the left plot and the right plot is that both of these are quantum dimers, but bismuth ytterbium germanate is an isolated diamond magnet. You can see the difference. On the left hand side, the triplet peak has dispersion, it's wavy. Whereas on the right hand side, it's entirely flat, depicting there's no interaction happening between these dimers. We made some cuts, so we go over, we make a cut along the energy transfer, and we see our little triplet peak. So this huge peak is the elastic transfer, and this tiny little peak is the triplet excitation. We look at this triplet excitation in isolation, we separate it out, and after we separate it out, we try to fit it. We use simple Gaussian modeling to get an idea of the exchange interactions between the ytterbium atoms. What is the exchange strength? What are the parameters? We do some fitting and we find out this is an anisotropic system. So in the XY direction, we have almost half the exchange strength as in the Z direction. Now what's interesting is, in 2023, when Mohanty performed their measurements, they never did neutrons. This is the beauty of science and physics, where we perform an entirely different measurement and get an entirely different conclusion, but it matches exactly the same to the heat capacity that was done in 2023 on the same material. So using these different techniques, we can obtain these parameters and physics checks out, it works out. So bismuth ytterbium germanate, which is actually bismuth 1.2 ytterbium 0.8 germanate, is the first finding of an isolated quantum diamond magnet in rare earths. This is the first time we've had an isolated quantum diamond magnet, which is really important again for quantum computers, because if quantum diamond magnets are the simplest possible quantum magnet, isolated quantum diamond magnets are even further simpler than a quantum diamond magnet. Very important for computational purposes. Well, anyway, this was the story of bismuth ytterbium germanate, where the ytterbium atoms are trying to dance in an entangled manner, whereas we've got the bismuth trying to break them apart. I hope you feel entangled. We've got the research paper over here if you're interested, and if you are entangled, please feel free to ask any questions. Thank you very much. I'll use this now.
Thank you, Rashid. So now the stage is open for the question. If you have any questions, you can ask to Mr. Rashid. Yes? Anybody? Okay, Rashid, I have one question.
Yes, please.
Can you synthesize the material which you are showing in the slide 29?
So the only material that works over here is bismuth ytterbium germanate. So that's very interesting. So what we did was, we sent in stoichiometric amounts of bismuth oxide and ytterbium oxide. the material automatically forms in this side-stuffed manner. So we never put an extra 20% bismuth in our reactants. The compound, when we perform our retooled refinement from the neutron diffraction and we refine the occupancies of both of these sites, we find that bismuth is actually 20% extra than it is supposed to be, and ytterbium is 20% less than it is supposed to be.
Okay, you have shown on a slide number, I think 28.
Yes, this is.
Some is splitting, some maybe, yeah. So you have shown this splitting. So how can you confirm that this splitting is because of the scattering and because the splitting is also the material is formed. So it is maybe because of the some when the machine is doing some background noise and also some structural things. So what you will say about this splitting?
So if I'm getting it correctly, you're referring to the splitting that is happening between the big peak and the small peak?
Small.
Oh, so like the multiple things that I'm...
Yeah.
Oh, so this is actually based on the temperature. So this is also a very good question. So you can see that as we decrease the temperature, so the red plot where the triplet peak is almost invisible was taken at 100 Kelvin. So that's a high temperature measurement. Whereas as you keep on reducing the temperature, what happens is ytterbium's electrons need to be entangled. We need a low temperature environment for that. So as you keep on reducing the temperature to a lower and lower value, you can see that the intensity of the triplet peak rises. Whereas the elastic peak stays very still. So the big peak, irrespective of the temperature, has the same intensity. But the inelastic peak, the triplet peak, will get a spectral weight increase on a decrease of temperature because more and more electrons are able to access the dimer ground state.
Okay, nice talk, Mr. Rachid. Now I would like to invite Dr. Manoj Giri from Dolat Ram College, DU. Now he will present his talk on the spectral parameters of orange green in aqueous solution. Now over to you, Dr. Giri.
Good morning, everyone. I'm thankful to the organizers to give me this opportunity to present my current work on this stage. We are working on dyes. Dyes are those organic compounds which absorb in ultraviolet, visible and near infrared vision, and they have potential applications in every scientific and industrial field, such as in photonics, laser dyes, liquid crystal display, and etc. We are concerned here mainly on azo dyes. Azo dyes can be easily identified by among the dye. Those dye have N double bond N. Those dye which have N double bond N are known as azo dyes. PDF file. This one, azo dyes dominate the dyes class. Here about 60% of all dyes are azo dyes. We have taken here orange green, also known as acid orange 10. And we have just here, we have done here, this is the molecule, big molecule. We have taken first its UV spectra. 3 peaks we are observing here, and lambda max we observed here at 480 nanometer. At various concentrations we have taken it, and by observing or analyzing it, first we are going to find the optimum concentration. Optimum concentration here from the graph, we can say that it's not this highest peak. Red peak will showing us the optimum concentration, because other 2 peaks going beyond 3, beyond the range. So these are not the optimum concentration range or optimum concentration, and not from this. When we taken the fluorescence spectra of this dye from this, when we taken the multi-skin spectra of this dye, then carefully analyzing it, we are finding here that 40 microam is the optimum concentration. And by doing this, we can find the Stokes shift. Stokes shift, or means energy loss, is near about of 87 nanometer. By analyzing the absorption and fluorescence spectra of this dye, we can say that 40 microam is the optimum concentration for the spectroscopic study of the compound in aqueous solution, and also various parameters of scientific values such as extinction coefficient, oscillator strength, and dipole moment, and many more determined from this. And we carried this study at JNU in the lab of Professor Sogan-sen. This is the recent publication. The purpose of this to find the potential application of this dye, particular orange green, as a food product, or is it possible to make it as a laser dyes. Further investigation is needed for this, and we are trying to bind this dye with protein and micelles. At present we are doing this. It's our present work, which we are working on this. So if you want to ask anything about it, you can ask.
The peak is showing about 575.
Yes, sir. 567.
What exactly this peak representing? So this is not a sharp peak.
Not sharp peak.
Just broadband.
Yes, broadband. It's a broad emission peak. So enhancement is needed here. To make it clear, we need either protein binding here or some another doping, by which we can make it, we can say that we can confirm after further investigation. Because it's not, it's a weak fluorescence, low fluorescence. So just now it is the idea, you are getting here some emission.
So this is 40 micromolar.
Micromolar.
So what is the maximum detection limit? Maximum means 40 micro nanomolar, 10 nanomolar.
Not possible. Because when we observe this graph, then here from this, this is the peak at which we are getting it. At another peak, this is the, you can say that very distorted peak. And another peak have low intensity comparative to this. So there is a problem in this, it shows low fluorescence. So we have to enhance its fluorescence either by adding here protein, by binding it with the protein. We are working on that.
The white peak cannot indicate the particular thing. So it's a confusing.
So we are saying, I am saying that further investigation is needed here.
You have to improve it.
Any question from participant side? Yes. If there is no question, so sir, thank you for your nice talk. And now I would invite Ms. Srishti Kuswa for the her presentation. She is coming from Oriental University, Indore, and she will deliver his talk on a eco-friendly lignosulfonate PVA-based biopolymer electrolyte films for energy storage device.
Good morning, everyone. Good morning, dignitaries. Thank you for giving me the platform for that explain my presentation ideas and my research work. Actually, I am doing the work in a Oriental University, Indore, in a eco-friendly lignosulfate PBA-based polymer electrolytes film for energy storage device. Generally, we all know the main problem is that कि हम एनर्जी तो प्रोड्यूस कर रहे हैं, स्टोरेज के लिए नए नए डिवाइसेस और मटेरियल्स हम नए नए अभी भी रिसर्चेस चलते जा रहे हैं. तो उन रिसर्चेज में जो बायो वेस्ट प्रोडक्ट्स होते हैं लाइक दैट लिग्निन हुआ, तो हम क्योंकि वुडन तो हम यूज़ कर रहे हैं एज अ कंस्ट्रक्शन, एज अ मटीरियल, एज अ अदर थिंग्स में, बट हम इसका अदर वेस्ट मटेरियल का हम यूज़ कैसे कर सकते हैं. सो आई एम यूजिंग हियर लिग्निन, दिस इज कंपोनेंट ऑफ कैल्शियम लिग्नोसल्फेट, है ना, विथ मैच विद द पीबीए के साथ में जब पीबीए के साथ जब हम इसे डिसॉल्व करें तो कुछ नया प्रोडक्टिव इनोवेटिव मटेरियल हमें फाइंड हो रहा है. नाउ आई एम टेलिंग यू अबाउट माय स्लाइड्स. इट्स अ रिन्यूएबल एनर्जी सिस्टम. इलेक्ट्रिक व्हीकल्स में हम यूज़ करते हैं, पोर्टेबल डिवाइसेस लाइक इलेक्ट्रॉनिक्स, मोबाइल फोन्स, इनमें भी इन चीज़ों का हम यूज़ कर सकते हैं. बेसिकली मेरा जो रिसर्च एक्सपेरिमेंटल वर्क है उसके मैंने ऑब्जेक्टिव्स में फाइंड आउट किया था कि भाई मैं सिंथेसाइजिंग बायोपॉलीमर बेस्ड इलेक्ट्रोलाइज फिल्म बनाऊंगी, अपार्ट फ्रॉम दैट इन्वेस्टिगेट आयनिक कंडक्टिविटी इन दैट वन एंड स्ट्रक्चरल कैरेक्टराइजेशन लाइक एक्सआईडी और ये सब इसमें करके दिखा दूंगी. अब फर्स्टली है एनर्जी स्टोरेज डिवाइस. तो ठीक क्या बनाते हैं, तो फर्स्टली एनर्जी स्टोरेज डिवाइसेस होती क्या है. सो डिवाइसेस दैट यूज फॉर लेटर यूज फॉर कॉल्ड द एनर्जी स्टोरेज डिवाइस, जो कि केमिकल एनर्जी कन्वर्ट करें इलेक्ट्रिकल एनर्जी में. These energy basically बैटरीज, सुपर कैपेसिटर्स और फ्यूल सेल्स से मिलती है. मेजर कंपोनेंट्स डिवाइसेस के अंदर आते हैं इलेक्ट्रोलाइट्स, सेपरेटर एंड इलेक्ट्रोड्स. इलेक्ट्रोलाइट्स बेसिकली मीडियम फॉर आयन ट्रांसपोर्ट बिटवीन द इलेक्ट्रोड्स होता है विद इन क्रिटिकल इन डिटरमाइन डिवाइसेस इफिशिएंसी इन उसकी स्टेबिलिटी पे बात करते हैं. सो इट्स वेरी इंपॉर्टेंट पार्ट ऑफ एनर्जी स्टोरेज डिवाइसेस. इसमें जो मटेरियल यूज़ किया है पीवीए, जिसे मैंने सिंपल सॉल्यूशन कास्ट टेक्निक के थ्रू यूज़ किया था, जिसको 80 डिग्री टेम्परेचर पर मैंने इसे डिसॉल्व किया था. क्योंकि बिफोर दैट हम बात कर रहे थे तो वो कहीं ना कहीं डिसॉल्व नहीं हो रहा था. काफ़ी सारी स्टडीज़ और हमने लिटरेचर पढ़ा तो उसमें 70 to 80 के बीच में इट विल बी कैनली ईजिली डिसॉल्व. तो बाय हिट एंड ट्राई मेथड वी यूज़ देयर एंड 80 पे ही हमारा पीवीए डिसॉल्व हो रहा था डीआई वाटर के साथ में. अपार्ट फ्रॉम इसमें हमने कैल्शियम लिग्नोसल्फेट यूज़ किया है विथ सोडियम क्लोराइड सॉल्ट ऐड किया था. तो फर्स्टली जो पीवीए है 0.50 ग्राम लिया, इसके साथ में हमने लिया पीवीए को डिसॉल्व किया फिर 80 डिग्री टेम्परेचर पर. क्योंकि बिफोर दैट मैंने हिट एंड ट्राई 7 to 8 स्लाइड्स बनाई थी, इसमें पीवीए डिसॉल्व नहीं होता दिख रहा था, लेकिन जब हम उसको कास्ट करें तो उसमें कहीं ना कहीं वाइट कलर के एक लम्प, एक ट्रांसपेरेंट से मॉलिक्यूल्स दिख रहे हैं. तो उसके बाद जब हमने इसको 80 डिग्री पर सेट किया इट कैन बी इजीली डिसॉल्व एंड ट्रांसपेरेंट. इसके बाद इसमें ऐड किया हमने लिग्नोसल्फेट का, देन हीट अप इन 1 to 2 hours मिनिमम ऑफ दैट वन, देन एडिंग द सोडियम क्लोराइड सॉल्ट विद दैट. आफ्टर दैट स्टोरी वी विल कास्टिंग द dish film and casting the film. After that actually it will be very flexible. Here I can find out. इसका जब मैट्रिक्स प्लॉट किया मैंने z और z के बीच में वो जो फॉर्मूला आता है T/RV into A नॉर्मल फॉर्मूला, तो मैट्रिक्स प्लॉट में मैंने देखा इसको जूम आउट करेंगे तो यहाँ पे एक RV फेलोशिप क्रिएट हो रहा था जिसकी एक्स एक्सिस और वाई एक्सिस इमेजिनरी और रियल पे बेस्ड है. इसके बाद जब मैंने सॉल्ट का जो ग्राफ बनाया इट विल बी हाई और इसका जो कंडक्टिविटी मटेरियल आ रहा है 20 पे आ रहा है. तो कहीं ना कहीं 5.028 into 10⁻³ पे मुझे मेरी कंडक्टिविटी फाइंड आउट हो रही है. इसका जब मैंने ग्राफ प्लॉट किया तो मुझे यहाँ पर 60 मटेरियल में 60% वेट मटेरियल में मुझे यहाँ पर अपनी कंडक्टिविटी प्रोड्यूस, इसके बाद थोड़ा सा स्लाइट डिक्रीजिंग गया था. तो मुझे यहाँ मैक्सिमम मेरा टारगेट था, मैंने जो फिल्म क्रिएट करी थी उसमें कहाँ पर मेरी कंडक्टिविटी प्रोड्यूस हो रही थी आई कैन इजीली रेक्टिफाई फ्रॉम दैट. इसके बाद बल्क रेजिस्टेंस के बाद डिक्रीजिंग होना शुरू होता है. एक्सआईडी यूज़ किया इस मटेरियल के लिए. एक्सआईडी पावरफुल कैरेक्टर टेक्निक है, हम सभी को पता है, क्योंकि ये बायोपॉलीमर्स के पीक्स और उसके कैल्शियम इसकी जो ग्राफ बना है 2-3 का एंड इंटेंसिटी के बीच में जो मुझे ग्राफ शो हुए थे, ये दो ग्राफ मुझे शो हुए थे, हाई पीक शो हुए थे 30.17 from 23.737. तो ये जो पीक्स थे हमारे क्रिस्टली बिहेवियर को शो कर रहे थे कि हमारा ये स्ट्रक्चर बेस के साथ में कैसे क्रिस्टली शो कर रहा है. इसके जो शार्प पीक के जो आ रहे हैं आपको दिख रहे हैं यहाँ पे शार्प पीक्स, वो आपके इंटेंसिटी के बिहेवियर को पीक्स को डिफाइन कर रही है, ठीक है। इंटेंसिटी रिफ्लेक्ट्स द डिग्री ऑफ क्रिस्टलिटी। क्रिस्टलिटी की बात हो गई थी, अब हम जाके आगे चलते हैं एक्सआईडी पैटर्न में। जब सॉल्ट वो विदाउट सॉल्ट कर रहा है, पीबीए के साथ में जब मैंने सॉल्ट ऐड किया तो इसकी अमॉर्फिसिटी दिख रही है। ये जो ग्राफ आ रहे थे देखिए, इनकी पीक्स के बाद हम ये डिफाइन कर सकते हैं कि इसकी जो अमॉर्फिसिटी थी वो बढ़ गई दोनों मटेरियल्स के बीच। और ये ब्रॉड पीक ऑब्जर्व, जो ब्रॉड पीक है वो ऑब्जर्व हुई 19.393 पे और 32.166 पे, जो जनरली डिपेंड्स कर रही है कि जो मटेरियल हमने यूज किया है पॉजिटिव अमॉर्फिसिटी है, स्ट्रक्चर इंटरमॉलिक्यूलर इंटरेक्शंस बिटवीन द हमारी मटेरियल और पॉलीमर इलेक्ट्रोलाइट्स के बीच में आता है। Now finally I am going to the next step, that is the FTIR. FTIR analysis confirm interaction between the जो हमारे सॉल्ट साइड पॉलीमर्स था और सॉल्ट था NaCl का, उसके बीच में इनके बीच में जो शिफ्टिंग हो रही थी पीक्स की, वो ये आपका OH आयन को दिखा रहा था कि भाई ये शिफ्टिंग हो रही है पीक की, क्योंकि एक पॉजिटिव रिस्पॉन्स दे रही है। आई एम नॉट सेइंग कि इट्स अ वेरी गुड और वेरी बेस्ट प्रोडक्ट, बट स्टिल देयर हैव अ चांस टू समथिंग ग्रो। इसके बाद इसकी शिफ्टिंग है, हाइड्रोजिक से जरूरत बता दी है। इसकी शिफ्टिंग के साथ में हमने बताया कि कहीं ना कहीं इसके अंदर चांस है, होप है, हम मटेरियल को आगे यूज कर सकते हैं ब्रॉडली। इसके बाद कंक्लूजन में मैं आपको कंडक्ट करना चाहूंगी कि जो मेरा लिग्नोसल्फेट है पीबीए के साथ में मैंने सर्च किया है, दैट इज प्राइमरी बायोडिग्रेडेबल मटेरियल विद सोडियम क्लोराइड। इट इज रिफ्लेक्टिंग एज अ सॉल्ट थ्रू द फिल्म प्रिपरेशन प्रोसेस। सिंपल कास्टिंग मेथड्स जो हमने यूज किया था उसका रिजल्ट हमारा ऐसा आया है। इट वाज अ गुड साइन, आई थिंक सो। सो आई विल गो विद नेक्स्ट प्रोसेस फॉर फर्दर प्रोसेस के इसकी कंडक्टिविटी, इसका बोर्ड के साथ में इसको आरबी को रिप्रेजेंट करेंगे कुछ ऐसा। थैंक यू। एक्नॉलेजमेंट में देना चाहूँगी डॉक्टर भास्कर भट्टाचार्य सर, बनारस हिंदू यूनिवर्सिटी में जो एनएमई में है, उनका काफ़ी सपोर्ट रहा इस कास्टिंग फिल्म को लेकर के। इसके अलावा डॉक्टर अंजी पॉलू हैदराबाद में, उन्होंने काफ़ी इसकी कैरेक्टराइजेशन टेक्निक्स में मेरी हेल्प करी। इसके अलावा मिस्टर शिवांग जो कि बीएचयू का रिसर्च स्कॉलर ही है, उसने एक्सआईडी और एफटीआर के ग्राफ्स के लिए मेरी काफ़ी हेल्प करी, तो थैंक्स टू दैम।
Thank you, Ms. Shrasti.
Yes, ma'am.
So now this is open. You can ask any questions. So if you want to ask.
Can you please go back to your X-ray plots? Right, so you've shown these two plots.
Yes,
Yeah.
yes.
Is there any fitting involved here? Because so what I'm seeing over here is this is a spline of all of your data points connected together, which gives it this weird shape to the peaks. This is not really observable if you use just the data points in your analysis. Did you perform any read-field refinement?
No, sir.
Okay. All right. So there's no read-field refinement done.
ये क्रिस्टलाइन है, अमोर्फस है।
सर ये मटेरियल जो है मेरा अमॉर्फिसिटी दिखा रहा है नेक्स्ट स्लाइड में, देखिए ये जो मटेरियल है मेरा अमॉर्फिसिटी है, तो कहीं ना कहीं
मटेरियल इज गुड फॉर द एनर्जी स्टोरेज, अमोर्फस क्रिस्टलाइन।
दे आर द टोटली अपोजिट फ्रॉम दैट। इफ द क्रिस्टलिटी इंक्रीज होगी तो अमॉर्फिसिटी डिक्रीज होगी, अगर क्रिस्टलिटी बढ़ेगी डिक्रीज होगी तो अमॉर्फिसिटी बढ़ेगी।
मैं ये पूछ रहा हूँ कि आप क्या सोचते हो कि एनर्जी स्टोरेज के लिए जो मटेरियल
क्रिस्टलिटी का डिक्रीज होना और अमॉर्फिसिटी का बढ़ना इज इम्पॉर्टेंट।
He's asking that which type of material, amorphous or the crystalline material, is applicable for the energy storage devices.
अमॉर्फिसिटी जिस मटेरियल की सबसे ज़्यादा होगी, इट इज़ सुटेबल फॉर स्टोरिंग द डिवाइसेस।
कुछ मेजरमेंट किया आपने?
सर मैंने थ्रू द फार्मूलाज ओरिगन पे बना करके ये सारे ग्राफ लगाए थे और थिक फिल्म बनाई थी।
कुछ मेजरमेंट किया, कुछ साइकिल टेस्ट की?
बोर्ड प्लॉट मैं ड्रॉ कर रही थी बट इट वाज नॉट कंडक्टेड कल तक, तो उससे मेरा आरबी का जो है वो ट्रस्टेबल रिजल्ट्स निकल के आ जाते हैं।
एक आपने जेड
हाँ, नाइक्विस्ट प्लॉट ड्रॉ किया था।
उससे क्या समझा मटेरियल, क्या इंपॉर्टेंस है इससे?
एक्चुअली जब हम प्लेन की बात कर रहे थे, जब पीवी और लिग्निन सिंपल लेके चली थी मैं, तो यहाँ पर मुझे
समझ में आ रहा है। इन ग्राफ से आपको क्या समझ आया?
इन ग्राफ से ये है कि जब मैं मटेरियल नॉर्मल पीवी और बेस लेके चली थी तो उसमें कहीं ना कहीं आरबी आ रहा था, लेकिन जब मैं क्रिस्टल सॉल्ट डाल देती हूँ तो उसकी क्या है वो अपने आप ही रिएक्ट करने लग जाता है। ये देखिए सॉल्ट डालने के बाद इसका जो कंडक्टिविटी है वो मुझे रिकॉग्नाइज हो रही थी यहाँ पर तो इट 5.038 इंटू 10⁻⁻⁴ जो सिनेस मेरा निकल के आया था वो यहाँ पर निकला
है। ये देखो बैटरी में साइकिल होता है,
हाँ,
चार्जिंग
exactly.
डिस्चार्ज। So what kind of do you feel the beneficial or your material for battery storage or not?
It's good for the battery storage devices.
आपको कंपैरिजन दिखाना चाहिए दूसरे materials का।
Sir, my next I will look into it in the next presentation. Thank you so much.
Without comparison से difficult।
ठीक है sir, next मैं इसको भी add on कर लूँगी. Thank you so much.
Yeah, I still had a question. So just on this slide itself actually, so you've shown that when you add salt, your impedance significantly reduces. I mean, the top graph is on the order of 10 to the power 6, but the bottom is just 10 to the power 1. So just by adding salt, you've reduced your impedance by folds of magnitude. Whereas on the other side, the bottom part is the crystalline material, whereas just PVA plus lignin is amorphous. So do you still stand by your claim that it's better to have an amorphous material?
Yes, it's a better amorphous material due to the इसकी जो crystality के साथ में जो मैंने peaks बनाए थे conductivity को लेकर के वो corrected थे. Thank you so much.
Thank you, Ms. Rashmi. Now I would like to invite Dr. Mayank Dubey from Shivaji College, DU, and he will present his talk on a collisional properties of highly charged ions in a strongly coupled plasma environment. Sir, now stage over to you.
Okay. Okay, good afternoon everyone. Today I will be giving presentation on the topic collisional properties of highly charged ions in strongly coupled plasma environment. Okay. Now overview of the talk will be as follows. Firstly, I will discuss the need of theoretical atomic calculation for reliable atomic data. Then I will discuss atomic structure calculations using the relativistic configuration interaction technique. After that, I will discuss dense plasma calculations using the IC-SFAM model. And in the end, I will discuss influence of plasma environment on the collisional calculations of highly charged ions. Okay, so why do we need theoretical atomic structure calculations? These are needed for the prediction and analysis of observational data from various space missions. It is also required for the determination and examination of physical conditions such as densities and temperature in present and future fusion plasma experiments. It is due to the growing demand of large and accurate atomic data, various powerful methods have been developed. And using these methods, one can calculate energy levels, radiative rates, and collisional cross sections. Okay, now we use the method which we use is relativistic configuration interaction method. In this method, the Dirac-Coulomb Hamiltonian for the n electron atom or ion is represented in this form, where the 1 electron Hamiltonian is given by this term. And in this 1 electron term, Hamiltonian, the first two terms depict the kinetic energy and the last term depicts the Coulomb potential of the nucleus. Now in this, we construct atomic state function for the n electron system as a linear combination of configuration state function, which has this form. Okay. Now apart from energy levels, oscillator strengths and transitional probabilities are also calculated. And it is this oscillator strength is related to the transitional probability with this relation, and the lifetime for a level is the reciprocal of the sum of the all transitional probabilities. Now to model our atomic structure calculations in the dense plasma conditions, we use IC-SFAM model. Now in this IC-SFAM model, this ion is confined at the center of the spherically symmetric cell, which contains the adequate number of electrons to sustain the charge neutrality of the system. Now to model this dense plasma, we use the potential of our collaborator Lee and Rosemes for Sorbonne University, France. Okay. Now
in this graph, we have compared our theoretical result with the recent high resolution measurements of Birsdorfer et al. And our theoretical calculations were in better agreement with the experimental ones. And this experiment was conducted in the dense plasma conditions. Now, we have also calculated the plasma energy shift for 1s3p singlet p1 or to 1s2 singlet s0 transition of helium-like argon ion. Okay. Now, in this graph, you can see with the increase of electron density, our plasma shifts are increasing, whereas when we increase the plasma temperature, our shifts are decreasing. This is due to the fact that with the increase of temperature, the free electrons are distributed farther away from the nucleus, and thereby the screening is weakened. Okay. Now, we have also calculated plasma energy shift for the same transition 1s3p singlet p1 or to 1s2 singlet s0 for helium-like iron case. Okay. Now, in this case, the same behavior is obtained. It is plasma shift is increasing with the increase of electron density and decreasing with the electron temperature. Whereas now the shift is more pronounced for argon case, which is having low jet, as compared to the higher jet iron case. This is due to the fact that Coulombic attraction between the electron and the nucleus increases with the increase of nuclear charge. Okay, now in this graph we have plotted the variation of transition probability of 1s to 2p 3/2 transition of hydrogen like oxygen ion as a function of free electron density. Here, with the increase of electron density, this transition rate is decreasing. Now, there are two collisional processes which we study are photoionization and electron impact excitation. Now, what is photoionization? In photoionization, a photon is incident on an atom, and a sufficient if this photon has sufficient energy, so electron is stripped off from that atom, and we get this H nu plus X goes to X plus plus 1 free electron. Okay. This is the photoionization. Now, the another collisional process which we study is electron impact excitation. When an incident electron collides with an atom or ion, energy transfer takes place, and which excites the atom from initial state I to final state F. Okay. Now, the formulas, mathematical relations which we use are, this is for photoionization cross section, and the inverse process is radiative recombination cross section. This is related to the photoionized cross section with this relation, and the excitation cross section for initial state to final state is related with this collision strength with this relation. Now, in this plot, we have shown the variation of ionization potential depression of one state of hydrogen-like ions. These are hydrogen-like carbon, oxygen, aluminum as a function of free electron density at a fixed temperature of 200 electron volt. Okay. Now, for a fixed temperature of 200 electron volt, the ionization potential depression is significantly increased with increasing electron density and becomes less pronounced with the increase in nuclear charge. For example, the ionization potential depression is about 1.74 electron volt for helium like hydrogen like this carbon case, and 0.68 electron volt for hydrogen like aluminum case, for a fixed electron density 2 into 10 to the power 23 per centimeter cube. Now, in this graph, we have just studied the variation of this photoionization cross section as a function of photon energies at different densities. Okay, for the isolated case, this was just monotonically decreasing, but in the case when it is immersed in a dense plasma condition, we get just decreasing, then it increases, then further decreases. That this lower point is known as Cooper minima. Okay, in this graph we have plotted the variation of collision strength as a function of incident electron density for 2s half to 3p half transition of hydrogen like silicon ion. For the isolated case, this is black bold line, and other cases when ion is immersed in plasma at electron density 2 into 10 to the power 23 per centimeter cube, and 1 into 10 power 24 per centimeter cube, and with the temperatures 200 and 1000 electron volt. Now comes the conclusion. Atomic data such as energy levels, decay rates, and cross-section are essential for the modeling and diagnostics of astrophysical and laboratory plasmas. Now, including plasma screening effects enables accurate interpretation of spectral lines and reliable diagnostics of plasma temperature and density. These studies also provide crucial atomic data for fusion fusor devices like ITER. Now these are the list of the references. Thank you very much for your attention.
Okay, thank you, Dr. Bayan, for such a nice talk. Now the stage is open. You can ask any question. Yes? Yeah. So he's the only one who is asking
That's
question. Yeah,
it's open. I had two questions actually.
Okay.
One thing that I noticed interesting was, so all of your atoms that you're taking, I think you're making in a single electron case at the very end. So for example, oxygen was 7+, carbon 5+, so on and so forth. Argon, on the other hand, was 16+. Is there a specific reason that argon has 2 electrons left in your studies?
Yes, yes. That is, if you are having any particular argon ion, suppose argon atom, ion is obtained when you just strip off electron using high intensity laser. If one electron is stripped off, this is argon plus. If 2 electrons are stripped off, it is argon 2 plus. Yes, right. And 16 electrons are stripped off, that is helium-like case, helium-like argon. Okay.
So I mean, I totally understand. It's just
different ionization stages are possible in a tokamak reactor or this. You inject this atom as an impurity, and due to high temperature, various ionization stages are possible there, and you just reduce that ionization stage by its spectrum, analyzing the spectrum. Okay.
Sorry, I think I must have not said it correctly. So what I meant to ask was, all of your other atoms that you're testing, you keep on ionizing them until there's just one electron left.
No, different ionization stages are possible. We can also study helium-like, beryllium-like, carbon-like, neon-like argon, sodium-like argon. Different ionization stages of the atom are possible.
I'll ask you afterwards. My second question was, so you had this description where you were separating out between an isolated case and an immersed case. Could you please explain? I have no idea what that
okay, just like isolated case means consider the simple case of hydrogen atom. Okay, for the isolated case, your Hamiltonian is just a kinetic energy term plus potential energy term. Okay, p square by 2m plus z e square by 4 pi epsilon r. Okay, when you just in realistic conditions, there are different type of plasma environments. There are strongly coupled plasma environment. There are weakly coupled dusty plasma also occur in the space. Okay, if you consider the case of the interior of the Jovian planets or initial confinement fusion, this is the case of strongly coupled plasma. Okay, in this case, this isolated model does not predict the results which were studied experimentally. I have also shown the case of helium-like fluorine ion, which was studied under dense plasma condition. Now, in that case, due to the presence of this environment, some perturbations should be there. It should be different for this electron at this nucleus. If there are intervening electron 10^23, then this attraction between this electron and this nucleus will be screened by the intervening free electrons. Due to this, we have modeled this problem with, we have also incorporated another potential term that is IC-SFAM model. Okay, due to this, when this model was proposed, then it was tested with the experimental data, and a good agreement was achieved.
Lovely, that's wonderful. Okay. Just one last thing. So your plasma that you're making, is it of the same atom that you're studying, or is the plasma of another element?
No, it can be of the same element also. If you just this ITR or chamber, there are different millions of atoms. Then you just bombard the
it's a
laser.
central chamber that you ionize.
हाँ.
Okay, okay, thanks very much.
Okay, thank you very much, everyone.
Actually, I'm a little confused your presentation. So could you please connect your presentation with the theme of the conference?
No, it is actually for fusion is also for green energy.
No, but you haven't mentioned anything and no indication that your research is it means the emerging frontiers in sustainable function and advanced materials. Neither you have the experimental nor the simulation, it's just a calculation theoretical.
Yes.
So, actually,
Best suited for this atomic engine.
But what kind of application do you feel
Sir,
used for?
by this we can predict there are different stars and different astrophysical objects. We cannot predict their temperature by using thermometer. By analyzing the light density ratios, we can reduce the temperatures, chemical composition of that distant star, and other things.
Any practical approach?
Yes. Yes.
In previous data, not yours, like you are doing that, not yours. Anybody have performed this kind of prediction?
Yes, I know also plotted shown the graph where dense plasma calculation for helium like chlorine phase was performed in that Lawrence Livermore laboratory, and our beautiful predicted data was in good agreement with that.
Okay, thank you, Dr. Mayank Dury, for such an informational talk, which is based on the theoretical part. And sir, actually we have one theme in our conference which is totally based on a theoretical process which relate to the astrophysics theme. So that is why he is giving his talk. So now I would invite Dr. Mahesh C. Meena from Rajdhani College, University of Delhi. He is present there. Dr. Mahesh C. Meena. I think he is not there, and if he will there, so he will be deliver his talk on characterizing the optical and electrical properties of gold ion implanted MOS2 thin film. Okay, so now I give this to the Ritika.
With this, the session comes to an end. I would like to sincerely thank you, Neeru ma'am, for chairing this session so effectively. Meanwhile, the poster presentations are ongoing at Hawa Mahal. You are all encouraged to visit and explore the innovative research work displayed there. Lunch will be served at 1 p.m. at Samarth Guru Ramdas Hall. We will resume with session 6 after lunch. Kindly be present in the auditorium on time.
Please go to the Hawa Mahal and you will get some exposure about the research work is going on across the globe, okay? And after lunch, we will be here again, okay? Thank you.
से PhD इनका मेजर हमसे ही है, तो हमारे डिपार्टमेंट में हमारे कलीग नहीं हमारे साथ ही तो जैसे वो उसमें इंस्टीट्यूट में बट जी हुआ मैंने कल आपको देखा सही आप देखना उनको इस डिपार्टमेंट में वो करती है
Good afternoon, everyone. I hope you all had a refreshing lunch. Now we resume the conference proceedings with session 5. We are honored to continue this session under the esteemed guidance of Professor Mahesh Kumar. It is my pleasure to introduce Dr. Mahesh Kumar sir from CSIR MPL New Delhi. Dr. Sharma is a senior principal scientist at CSIR headquarters and also a professor at ACSIR. He is completed his PhD in condensed matter physics from the University of Delhi and CSIR MPL and has over 15 years of research experience in advanced materials. His research interests include hydrogen technologies, 2D materials, organic electronics and energy materials. He has published more than 150 research papers and is actively involved in several major national missions. I now invite Dr. Mahesh Kumar Sharma to kindly deliver his talk. I like to call Neetu Verma ma'am to
फेलिसिटेशन भी आप बाद में कर देना, कोई बात नहीं, जब अपना जो पूरा कर लेंगे काम के दाम
I like to call upon Neeru Sharma ma'am to felicitate Dr. Professor Mahesh Kumar with a token of appreciation with a shawl. Please give a big round of applause. I would like to call Dr. Mahesh Kumar Sharma sir to please session the chair.
Good afternoon and welcome to this post-lunch session. We have our first speaker, Dr. Bharati from Delhi Technological University, and she is currently assistant professor and hope she will be associate professor soon. And she has done her postdoc from Max Planck University and PhD from IIT Delhi. I think MIT IIT probably. Malika with Malika. So she has been a recipient distinction in PhD and she was BSc inspired SCRB award. And her research is in the areas of 2D materials, gas sensing, memory devices. And let's hand over the dice to Dr. Bharti. I think ऊपर ही.
Am I audible to everyone? Am I audible now? कुछ increase or?
Connected with live streaming.
Oh, okay. Okay. This is a device. ठीक है. Thank you, Dr. Mahesh, for the nice introduction. And first of all, I would like to take this opportunity to thank the organizing team and congratulate them for this wonderful conference. And special thanks to Dr. Surendra Kumar for giving me this opportunity of showing the work that I am doing at Delhi Technological University. As sir has said that I am an assistant professor working in Delhi Technological University and I joined D2 in the year 2017. And I will be presenting the work which my first PhD student has established or has carried out during his PhD tenure from 2018 to 2022. So, The topic of my today's presentation is Engineering 2D Materials for High Performance Mechanical Energy Harvesting in Variable and Environmental System. As a topic itself is very interesting for all the students because we are using all the new 2D materials and we are using it for a very important thing, because you must be seeing and you must be following the news nowadays that how much fight is going on for the oils and everything to have the energy, right? So it is very important topic that how we can use these 2D materials to generate the energy which is being wasted in the environment. So what is the energy problem? The escalating energy demand, and which is fueled by the rapid technological advancement and the burgeoning population of our country and the world, has basically sparked the interest of the scientific community to look for alternative sources, right? Every time we need to search for new and new energy sources which are renewable, sustainable. So this is the energy problem, because we know that fossil fuels are finite and they are causing the environment a big threat, and we need to look for alternative energy sources. And the second of thing, definitely we need to look for these alternative resources, but definitely we need to look for an understanding that these alternative sources should be able to power limitlessly, right? Although there are various renewable energy sources that are being used, but we'll see all of them have certain limitations. So we need to look for certain energy sources, and because we know that there is a rapid growth in the personal and the continuous updation, and because of the continuous updation, every year we are replacing our gadgets, right? And that is also posing the concern because of the e-waste. So it is very important to have these gadgets being powered by some renewable energy sources. So what is the energy solution? The energy solution is a development of a nano generator which can utilize the energy that is present in the environment. And in this direction, there are various type of energy sources which are available, such as sunlight, the vibrations which are present in our day-to-day life as well as in the industry. Everywhere there are different kinds of vibration present, and the heat that is there in the environment or in the body, we can use them for generating the electricity. But the focus of today's talk is to use the mechanical vibrations which are present in our environment to convert it into the useful form of the electricity. So that is why I have highlighted this, and there are various applications of these different type of vibrations which can be used for remote and mobile monitoring, and they can be used for portable and wearable bioelectronic devices. So they have advantages, they are environmental friendly, they are maintenance free, and they can power the devices. So these are various type of energy harvesters. As it is there that we can see that photovoltaic device, we are all familiar with the photovoltaic device whose operation relies on the sun that we have most of the time. But definitely the circumstances, it is we have to put these devices or the conversion devices in the outside, and in certain weathers you can't use these powers unless you have a storage. You can't use these powers for the useful form. So that is why the photovoltaic device, although the conversion efficiency is good, but still it is not being used every time. Then we have the thermoelectric devices. The problem with the thermoelectric devices is that they have a very low conversion efficiency, and in these thermoelectric devices the temperature gradient is being used to convert into the useful form of electricity, because every time we need electricity to power various devices. So these piezo triboelectric devices, they are different kind of energy harvesters whose operation relies on the vibrations, right? And you must see that the intensity of the vibration can range from the various body motions that we have every time in our body, like our heart is beating, our diaphragm is vibrating, and the blood which is flowing inside the body can also be used for conversion into electricity. And the various like the motion of the car and vehicles on the road, as well as the machine which are there in the industry. So various type of vibrations can be converted into the electricity. So this is not limited by the weather, this is not limited by the time of the day. So that is why this is very useful. Although the efficiency of these devices is not very high, but using different specific kind of materials, the conversion efficiency can be increased. So what is a nano generator? It is nothing but a small type of device which converts the mechanical movement into the electricity, and as the name implies, it is not very big in size, but yes, it gives sufficient power to drive the nanoscale devices. So these are the various applications of the nano generator. They can be used for self-powered sensors like these touchpads, active sensors. They can also be used for monitoring sports devices, and the various applications where we can use this nano generator. So because we are mostly focusing that these are the various applications of the nano generator, but finally what is the principle behind these nano generators? What do we do to make a nano generator? What type of materials? Because ultimately if we are using a solar energy harvester, so definitely we need to have a material, because everything is material. Whether it is a chip, whether it is any optoelectronic device, everything is talking about a material, right? A solar cell is basically nothing, it is a silicon solar cell, it is a silicon material. So whatever type of device we are using, the material part is very important. So in these type of nano generator, there are certain suitable kind of materials which has certain property, and that property we say it is called as a piezoelectricity, although it is not new. Does anybody know from the student that when it was invented, when is the piezoelectricity invented? Who invented the piezoelectric effect from the students, if they know? किसने सुना है? From the students, is anyone who knows, or any name associated with the piezoelectricity? Quartz. Yeah, quartz is a naturally occurring piezoelectric material, and it was like the French physicists and brothers, like the Curie brothers, right? Right? So everybody must be knowing about Curie brothers. They basically first discovered the piezoelectricity in the quartz material, and it was in the year 1880. So it was long back that this beautiful effect and the very important effect was discovered, where certain different kind of materials having certain property of their crystal structure to show certain polarization when they are being stressed, or when you press this material, the polarization gets developed. Means one of the phase have the positive voltage and positive charges accumulation, and the other phase has a negative charges accumulation. So because of this charges accumulation on the surface, when you stress these material, so there is a potential that is being developed, and when you apply this potential to any load, definitely current will start flowing. So this is the way that the piezoelectricity works. But yes, there has to be certain conditions for the material to show piezoelectricity, that they should not have a center of inversion, or if they have a center of inversion, so means when you stress this material, they are positive, because a crystal is made up of the positive cation and the anion, right? So if you stress these material, these positive and the negative charges gets displaced, right? And because of this, you have this piezoelectric effect. So it was in 1880 that the Curie brothers discovered this piezoelectric effect, and you can see that when you are stressing this material, the voltage is there in the multimeter, right? And there is another effect which we call as an inverse piezoelectric effect. So what is the inverse piezoelectric effect? When you apply certain voltage to the material starts contracting and the expansion starts in the material. And this is the effect that we use in some of the electronic equipments like atomic force microscope, right? So these are the effects that we use inside certain devices. So this is the effect, and the efficiency of this mechanical to electrical conversion is decided by certain coefficients of these material. Because how good a piezoelectric material, there has to be certain property and the coefficients of those materials. So these are called as the piezoelectric coefficients of the material, where they relates the polarization where they relate the polarization and the stress that you generate inside the material and the electric field and the strain that is being developed inside the material. So these are the very basic properties of the material. And okay, so these are the traditionally found piezoelectric materials such as lead zirconate. Although these materials had a good piezoelectric output, but the problem is that they are brittle in nature and they have the lead in their crystal structure, which causes concern to the environment. So it was in 2006 that the zinc oxide was being used as a piezoelectric device, but still the conversion efficiency of these devices is very low. So as we know that everybody is running after the graphene discovery to find new and new material having different properties. So one of the properties of the transition metal dichalcogenides that they have intrinsically piezoelectricity in their crystal structure when they are in the monolayer. Because what are 2D materials? The materials, what are 2D materials? Right? These 2D materials are the layered material, right, having thickness in the range of the angstrom or like half, like the sub angstrom or right sub nanometer, right. So in this case, one of the 2D materials or the many of the 2D materials are these transition dichalcogenides such as molybdenum disulfide WS2, and recently explored magazines also show the intrinsically piezoelectric nature. So the advantage of using these 2D materials that they are good, they are mechanically very strong, they have a large surface to volume ratio, and in addition to these properties they can be combined with various type of devices and they have a good piezoelectric coefficients, and we can tailor the piezoelectric coefficients of these 2D material as well. So that is why we have just tried to use these 2D materials. And okay, so this is the second type of energy harvesting devices, because these are the two different energy harvesters. One uses the piezoelectricity and the other uses the triboelectricity. I think in our early childhood days when we were in the like 4th, 5th class, when a teacher was not in the class, we used to do certain experiments, like we were rubbing these scales on our hairs and we could just attract the piece of paper, right. This is nothing but the contact electrification, means when you rub two materials the charges are being developed, right. This is what we have seen, and especially in winters if you are wearing some silk clothes and these woolen clothes, you can see the moment you put your feet on the ground you have certain shock in the body. Although the triboelectricity is not considered a good effect from the human point of view, but still it could be used, everything can be used for the good purpose. So these are the nano generators which can utilize this negative effect into a positive outcome, right student. So what is a triboelectricity? When you rub two materials, when you bring these two materials closer together by various means, you can generate the opposite charges on the two rubbing surfaces. This is what is triboelectricity. So these are two, because in the case of a piezoelectric one material is enough, whereas in the case of a triboelectricity we need to have two contacting material, and based on the electron donating and electron accepting properties of these two materials, one will get the positive charge and other will get the negative charge, right. So these are the properties, and because of this the polarization will be developed on the two face of the material, and you can have the voltage that can be applied across a load and you can have the output. So this is the triboelectricity, and based on the device we can have a triboelectric nano generator. So this is the working mechanism of the triboelectric nano generator. Because every time we need to collect certain current, you need to have certain electrodes. So whenever we have two materials, we need to make the electrodes at the back side of the material so that the voltages or the voltages can be trapped. Sorry. So this is the working mechanism. Before the material they are not in contact, and the moment it is being contact, the electron clouds of these two materials, because what is a material? It is nothing but some distribution of atoms, and inside the atoms we have distribution of electrons, right. So whenever you are bringing these two atoms, these two materials together, there will be redistribution of the electrons, and you will have the charges that are being developed on the faces of the material. So when you start when you start develop, because of this polarization, when you just release a material, the potential is being generated, and because of this potential, the current will start flowing when you apply the load. And again, when this, because current has been passed, so again you press the material, the current will start flowing in the opposite direction. So in that case, you have a alternating voltage. So this is the understanding of the contact electrification. Whenever these two materials are away from each other, we can see that the electrons cloud of these two materials do not overlap. However, when these two materials are brought together, the electron clouds will start overlapping. I think it is not working on here. Okay, so when we have the materials are being brought together, because of the electron cloud overlap, the materials from the atom A, because here the shells of the material A are filled, and where we have the shells available to go to the atom B, and you can have the transfer of charge. So this is the way the potential is being developed. So he is the father of nanogenerator, Professor Zhongling Wang, and Professor Zhongling Wang developed the first nanogenerator in the year 2006, and after that the first triboelectric nanogenerator was developed in the year 2012. So he is the one who used this negative effects for the generation of electricity. And we can see from these publications, although this slide is slightly old, but you can see that there is a rapid increase in this area, and people are looking for this to have a sustainable source of energy. So that is why we thought about it, that we should also look for these effects. Although we started with the pure 2D materials, but the device fabrication was not easy. So we tried to incorporate these 2D materials in the existing polymer, because we want to enhance the piezoelectricity of the existing polymer. Because if you want to have a wearable device, you should have flexibility in the nanogenerator, in the device. So these polymers are good flexible materials, and one of the material is PVDF, polyvinyl difluorides. Although there are various polymers that can be used, but one of the polymer is PVDF, and we can enhance the piezoelectricity of these polymers by doing various effects while synthesizing and after that. So one of the method is, if you pole these materials, or if you synthesize these materials by using an electrospinning technique, or you dope these materials with some intrinsically piezoelectric material. With theoretically, it is already known that these 2D materials are piezoelectric in nature, and if we incorporate these 2D materials in these polymers, we can enhance the piezoelectricity. So in that case, we have biocompatibility, because although the lead zirconate, the traditional piezoelectric material, it has a very high piezoelectric conversion efficiency, but it is not suitable because it is brittle in nature, so we can't use it for the flexible applications, right? So that is why this polymers was used. So here we used flexible nanogenerator based on the polymer 2D material for mechanical energy harvesting. So these are the various properties of these polymers, and these polymers when synthesized, polymer is nothing but the repeated chain of some monomer. Here the monomer is CH2CF2, right? When these monomers are being arranged in a different way, you have different phases of the polymer, which we say as a copolymers, right? So there are various polymers that we have. One of the polymer is PVDF, and there are various phase, alpha, beta, gamma. However, this beta phase is found to have a good piezoelectricity in nature because of the trans-trans arrangement of these CH2 and CF2 chain of this monomer, right? So these are the various 2D materials. These are the various applications where we can use because of the various intrinsic properties. They are thin, they are mechanically strong, they are transparent, and it is theoretically predicted that when we change these, because what is the 2D materials and the transition metal dichalcogenates? You have a transition metal, you have a chalcogen atom. Here the chalcogen atom can change from sulfur, selenium, tellurium, and this is the complete transition metal, chromium, molybdenum, tungsten. So by mixing various combinations, you can see that as we move from chalcogen, the piezoelectricity increases. So this is our first thought of designing the 2D materials, where we systematically replace a chalcogen atom in the the molybdenum system. So this is the hydrothermal technique that we have used. These are the various steps. We have this polymer, then we mix it with some solutions and cast on a substrate so that we can have the freestanding polymer film. This is the way that we develop the flexible films. So this is one of the other technique where we are depositing the materials or the fibers, and the fibers are good piezoelectric in nature. So this is called as electrospinning technique. So by two methods we developed the nano generator. One is a drop casting method and other is a electrospinning method where we have flexible films of the PVDF polymer. So you can see that this is the film, and which is basically connected with some aluminum electrode, and you can see copper wires are coming out. And the student, because when we started this work we don't have the dynamic shaker. What is a dynamic shaker? It can tap the material at different frequency. However, at that time we just tap the material with a hand and we can see that there are the excitations we can see in the oscilloscope, right? So these are various samples because we want to compare the piezoelectricity of the bare polymer and the 2D materials filled polymers, right? So definitely when these are the complete series of the material and these are the piezoelectric output. The output is, there are two major outputs because to have the power you should have the voltage and the current, right? So piezoelectric output voltage is being obtained when you like put the nano generator in parallel with the CRO, right? So these are the output voltage, and we can see one of the thing that we observed here is that instead of because as I said in the starting that our objective is to increase the piezoelectricity. So as I said that when we move from the sulfur to selenium, the piezoelectricity theoretically increases. So we used MoS2, MoSe2 and MoSSC. Okay, MoSSC. So in the case of a molybdenum sulfur selenium, it is a very good study, and you can also try that when we replace one of the sulfur atom in the molybdenum sulfide with the selenium, in addition to the in-plane piezoelectricity, you have out-of-plane piezoelectricity, and these different type of materials are called as a Janus material. These are very different from the normal transition metal dichalcogenides, and whatever the theoretical case was, we observed experimentally as here, and you can see that these are the piezoelectric output that we have. So the device having the molybdenum sulfur selenium as the piezoelectric material, the highest voltage is being generated. So this is the piezoelectric current because we have the output and the current, output voltage and current that we have, and these are in similar trend that we observed for the earlier. So this is the because in order to have the accurate concentration, because concentration of the nanofiller is also important. In this way we have just varied the concentration of the nanofiller, and we observed that when we filled the polymer film with a 7 weight percentage of molybdenum disulfide, we obtained the optimum result. So these are certain samples that we made. So these are certain characteristics. I know the students, undergraduate students, they might be facing certain difficulty in learning this, but definitely you will know, because whenever you are making some material, you have to characterize those material by various means such as FTIR, XRD, and this is a PE loops, and these are certain morphological means by which we can say how is the morphology, and we can say as we are filling the material with more and more nanofillers, the roughness is increasing in these AFM measurements. So these are voltage and the current measurement, and we see that there is an optimum concentration as well as the optimum frequency of the shaker, that by which we can tap the material to have the best output. So these are just the result that we have. So again these are certain voltage and the current measurements. So further then we have used the nanofibers. Then instead of drop casting the film, we prepared the fiber. Again we have filled the polymer with the different kind of chalcogen atom, and we observed the 7 weight % is the optimum concentration by using the various XRD and FTIR. We have the characterization of these samples. So I just would like to, because I am running short of time, I would like to show the various applications that we are doing. So this is the result that you can see. The voltage and the current is maximum for the 7 weight percentage of MoSe2. So this is very important, how much nanofiller is important in the device. So we need to optimize all these. So these are the triboelectric, because after that we optimize the concentration, then we use the device to make a triboelectric nanogenerator. In order to have a triboelectric nanogenerator, we need to have another type of material. So here we have used PVDF filled with 2D materials and the nylon as a second triboelectric layer, and we observed that this nano filled PVDF shows the better output in comparison to this. So these are the triboelectric output in terms of the load, because when we apply the load as per the matching impedance, it is maximum for the maximum. Okay sir, I will just show the. Okay, so these are the various real-time applications of the nanogenerator that we have developed. So you can see that we can power a calculator, we can as well power these watches with the voltage that we have generated. But student, mind you that because it is a alternating voltage, so we need to rectify this alternating voltage to power any device, and there is a large drop in the efficiency of the voltage we are generating, because here we are generating around 300 volt as well in the hybrid device. So by using certain power management circuits, we can efficiently use these generated power to power these small scale electronic devices. By placing the nanogenerator at various points on a body, we can see that there are various kinds of signals that we can have, and we can utilize it for the health monitoring of a person. So these are the self-powered water system that because we want to split the water to generate hydrogen, right? So that needs certain power outside. So why not to use the water that we have, why not to use the power that we are generating? So we have made the self-powered system, and you can see that this is a dynamic shaker, and you can see there are bubbles coming in the system, which indicates that there is a generation of the hydrogen in the system. So this is the device that we have used for the motion sensor, because we are all surrounded by various kinds of motion sensor devices. And why not to, because in order to develop or sustainability, we need to conserve as well. So when there is no person in the room, why the electricity are being opened? So that is why it is very important to have the motion sensor devices, right? And these devices need certain power to manage. So in this case, we have used the TNG, the signal that is being generated by the TNG to power these motion sensors. So there is a, sorry, okay, it's not visible here, I think. It's not, okay. It's a video. Here we can see because we have the acquisition module and we have the processing system. So when the signal is being generated and is being compared by the processing system, that there is a light and the person has moved or moved over a nano sensor that is there incorporated in the roads or various places, so it will not show any light. Whereas in the case when there is no light in the room and the person has moved, it will show the light that is being there. So this is the power that we have used for driving these motion sensor is the TNG power. So this is another application that we are doing. We are removing the organic pollutants from the dyes by using the power that we have generated by the TNG. And this is the recent work that we have, because ultimately whenever someone is moving, then only we have the power, but we want to store that power. So in order to have a self-powered systems, we need to have a storing unit as well. So we have used this laser-induced graphene and this PVDF BTO as a matrix to power or to store the energy that is being generated in a micro supercapacitors, and this work is in just initial stage. Okay, this is my team at Delhi Technological University. 4 of the PhD students have been awarded, and this is the ongoing student list. And I am really thankful to my supervisor from IIT Delhi, because of which I am here, and my collaborators at Max Planck and the various funding sources. And thank you. And I am really sorry.
Thank you, Dr.
Bharti, that's a wonderful talk, and I think a lot of people have learned about piezoelectricity and treadable electricity and your TNG materials. Let's have one or two quick questions if somebody has. सबको समझ में आ गया? मैं पूछूं सवाल?
I think he wants to have. Yeah.
I saw the device you had, which was a water split.
Yeah.
You said it was self-powered.
Yeah.
I'm not entirely sure how that works.
No, because in order to have this electrocatalysis, you want to have a catalysis. For catalysis, you need certain source.
Right.
If it is a photocatalysis, you will have the sun as a source. But if it is being powered, if it is electrocatalysis, you need certain voltage and or current, right? So that is being given by the nanogenerator device that we have.
So, well then, it wouldn't be considered self-powered because you would still need some external vibration.
No, but these are the various vibrations that are available in the environment. They are going waste, right? We don't need any source here.
I suppose it's semantics. I mean, I wouldn't call a solar cell self-powered. I would call it solar powered. So I wouldn't call a piezoelectric material self-powered. I would call it vibration powered.
Yeah, we can say because it is TNG powered.
I see. It's semantics. Thank you.
Yeah. Okay.
Any other questions? So just one question. What's the operating temperature, maximum and minimum that you can work on?
Sir, actually we have just operate them at the room temperature. We did not see on the higher temperature as well, but we can do. We are checking the humidities every time, every points. It is affecting the performance, but we have not checked the temperature. Because definitely polymers have a transition temperature, so I need to check as well. I will definitely check.
Thank you very much.
Okay, thank you.
Now I request our esteemed chairperson, Professor Mahesh Kumar sir, to felicitate Dr. Bharti ma'am by presenting her a planetary card. Please give a big round of applause. A memento and a certificate.
Thank you, sir. Thank you, sir.
मनिका के टाइम पे थी उसके पहले थी?
सर मैं मनिका मैम इनफैक्ट मतलब मेरी बहुत अच्छी सीनियर है. बट लेकिन हम उस समय बिकॉज शी पास्ड इन 2000 आई थिंक 8 में शी सबमिटेड हर थीसिस. हाँ हम लोग 8 में आए थे. हाँ जी.
फिर एक बार मेहता सर के पास मिलने गए थे.
ओके.
तभी मुलाकात हुई.
अच्छा ठीक है. अच्छा ओके.
Next we have Miss Tamuli. We have 10 minutes.
Good afternoon, everyone. My name is Gita Chamoli Mohan. I am a sustainability consultant. I'm a GRI certified sustainability consultant. I've done my master's in public administration from Columbia University in sustainability management, and I will be providing my take on what is the sustainability of the advanced materials that we are discussing today. So first of all, let's begin with the agenda. So I will be discussing regarding the circular economy. I'll basically be talking more about the sustainability aspect of it, and then moving over to its impact on the current sustainable and functional materials. I will also be discussing the thermodynamic limits of circularity, the thermodynamic framework for evaluating sustainability, adjusted scope 3 reduction percentages based on entropy. I will also be providing actionable pathways for researchers and corporations. Policymakers provide a future research agenda in my limited time frame. And also discuss the machine learning guided recyclable polymer design and self-healing composites from a thermodynamic lens. So first of all, let's begin with what is sustainability. Going more into the sustainability point of view, we have to realize that sustainable development is a very upcoming field. Basically, even the definition of sustainability started in 1972. And according to that definition, sustainable development is a development that meets the needs of the present without compromising the ability of future generations to meet their own needs. It basically has three principles. There are three guiding principles. One is the intergenerational equity, which says that you take it for granted that resources will be passed on from one generation to the other. There are physical limits, and that needs are always evolving. The needs always don't remain the same. They change over a period of time. There are three pillars to sustainability: environmental sustainability, which has more to do with planetary boundaries. There are 9 planetary boundaries, of which 7 have already been breached. So we need to take that into consideration whenever we are thinking about sustainability. The next is social sustainability, which has more to do with people. It has to do with the sustainable development goals. And last but not the least, we have the economic sustainability, which basically says that you must decouple prosperity and material consumption. Next, now before we go to the circular law and thermodynamics, let me advise you that initially there used to be the entire sustainability platform was a linear process. You take from the earth, you make, and then you waste it. But now, because it was realized that there was a lot of extraction that was happening, and from 1900 to 2019, there was a 5-fold increase in the extraction that happened. 7 billion tons of materials were extracted in 1900, but in 2019, around about 100 billion tons were extracted, and so there arose a need for a circular economy, and the concept of circular economy came into place. Now, basically, according to the circular economy, you do not just use the product, you have to reuse, remanufacture, recycle, and then there are different levels to it. So reuse, repair, remanufacture, recycle, and compose. As far as the circular economy is concerned, so circular economy was put forward as a panacea. It was said that if we move to a circular economy, that would result in a sustainable world. But however, over a period of time, there has been more discussion. It has been found that the circular economy is not so circular, and that has probably its roots, or most likely its roots, as far as physics is concerned. So the first law of physics says that matter can neither be created nor destroyed, and that forms the basis of the linear economy, because atoms will change from one form to the other. So as long as the atom remains, it's linear, it's good, it's sustainable, it's there. But that's not the case. The second law of thermodynamics says that there is entropy at each level. So basically, the second law says that every real process increases the total entropy of the universe. The entropy increases in isolated systems. So there'll be a low entropy economic process results in a high entropy product. And taking that into consideration, you realize that the circular economy also has its own limitations, and those limitations
those are the limitations of the circular economy. Basically, it says that there's no 100% recycling which is possible, energy is not recyclable like matter, irreversible dissipation of matter takes place, dependence on open system, renewable energy, and there is no perpetual motion and no infinite growth. Now, taking that into consideration, so the question arises that why is it that circular economy was proposed as a definition? Also because there was a linear take-make waste. However, over a period of time, it was realized that secondary production, instead of primary production, if you move to secondary production, it does save a lot of energy. Secondary production, the primary production, the percentage of sustainable materials, just bear with me a moment. So as far as aluminium was concerned, it was realized that if you reuse the aluminium that you've already produced and do not actually start producing once again, it results in a 95% increase in energy efficiency. As far as steel is concerned, it results in 70% energy efficiency and so on and so forth. So that's why the circular economy was proposed. What I'm suggesting is that even this measure, if you take into consideration the entropy aspect of it, this measure is not the real measure of sustainability. That you do have to take into consideration the entropy. You have to take into consideration the cumulative energy demand and the exergy analysis in order to determine the true sustainability of the material. And that has an impact on the sustainable functional and advanced materials that we're talking about. There was some kind of research that was done in it that tells us that as far as the sustainability gains are concerned, those gains have been overstated. So if you look at the So if you look at virgin PET and if you look at recycled PET, the recycled PET, if you just take only the carbon emission reduction, so currently sustainable development, any material is supposed to be sustainable as long as it meets the reduction in carbon dioxide emission criteria. Now, according to that criteria, if you use recycled PET, that is supposed to result in an efficiency of around about 55 to 67%. But if you take the entropy into accounting as well as cumulative exergy demands, you will see that that is highly misreported. That is only 41 to 52%. Also, if you see the PEF, it says according to the carbon reduction criteria, there would be 42 to 55% energy efficiency. But if you take the entropy adjusted scope 3 reduction, it's only 26 to 38%. So there's a lot of, so if we go only by the carbon dioxide emission reduction criteria, which is the current standard for sustainability, for measuring the sustainability of a product, we would be highly misreporting. There would be a lot of greenwashing. Any organization could say, we've done a little bit of recycling, and they could misreport it. But if you take into consideration the entropy adjusted scope 3 emission reduction, that will result in the correct reporting, and that also is an evolving field. I'm sure there'll be more in literature as well as more research that will come up that will change the nature of how sustainable a product is. Now this has obviously implications for the kind of sustainable materials that we will be talking about. Basically, all the research says that low ceiling temperature sustainable polymers are the ones that we should be focusing on. Secondly, there are the self-healing polymers. There should be more concentration on. So the self-healing polymers have to do with more to, there could be extrinsic systems-based self-healing polymers or intrinsic self-healing system-based polymers. This has obviously implications on the design of the product. The products should be such that they have a machine learning guided polymer designing, dynamic recycling process designing, and a self-healing under real service conditions. Finally, there are the actionable pathways for genuine circularity for researchers and policymakers, corporations, and educators. Researchers could go ahead with physics-informed ML for material design. Policymakers could add second law efficiency standards to EPR. Corporations could adopt cumulative exergy demand and entropy adjusted metrics. And educators could teach energy, entropy, and engineering curricula. And that sums up my presentation. Any questions?
Thank you very much. Nice presentation on circular economy, especially sustainability. Anybody else wish any query or doubt?
As you're from Colombia, I just wanted to know the US, how do you rate the sustainability? You must have seen the differences in the, how it has been for the past, if you lived there many years. So how it has been in the US and India, the sustainability quotient, or what's the difference between India and US?
There are fundamental differences as far as the ingraining of sustainability is concerned per se. So in New York, if you don't dispose of your waste properly, you get fined. You can't put your bio waste along with the other plastic waste together. If you do that, you are fined for it. So right at the level at which you're even disposing the product, sustainability is highly ingrained out there. Here, it's an emerging concept. It is quite. Considering the number of academicians, considering the amount of educated people that we have, there's probably more education than there is anywhere else. But at the ground, at the practical level, this requires everybody to be participating, it has to be done at every level, and definitely US is definitely more advanced than India. I mean, we are just getting where they are already. We'll probably be there soon. But of course, I mean, this struck me when I went there that, if you don't do the waste, that also costs.
This circular economy, there are a lot of materials, and if we brought into this again recycle reuse, the amount of energy which is being spent and the amount of CO2 which is being emitted, sometimes it is more than what we are.
Exactly the point. That is why carbon dioxide reduction is not the correct way. Just because it's reducing the carbon dioxide emission is not.
So only CO2 reduction should not be the only prospect in the circular economy and sustainability. A lot of other factors which are being considered.
Exactly. It's a field which is developing. As I said, sustainability, even the definition is just 1972. The Conference of Parties just started in 1995. Even within the field, there's a lot of discussion on what really is sustainable at the end of the day. Whatever is sustainable today is not going to be sustainable tomorrow. It's a changing framework, and this is my take on sustainable polymers and sustainable design. Thank you so much.
I think with this we end up this session.
With this, we come to the end of all the sessions of the International Conference on Emerging Frontiers in Sustainable, Functional and Advanced Material IC-SFAM 2026. Before we disperse, I would like to sincerely thank our esteemed chairperson for their valuable guidance. Now I request to kindly felicitate Professor Mahesh Kumar sir, where Neetu Verma ma'am. May I request Dr. Neetu Verma ma'am to kindly present the certification of token of appreciation to Professor Mahesh Kumar sir. Please give a big round of applause. I would also like to extend my heartfelt thanks to all the participants, speakers and organizers for their active involvement and for making this conference a great success. Thank you everyone for your active participation. I would like to inform all the participants that a culture program will be held at Chanakya Sabhagar, followed by the valedictory session as per the schedule. We will look forward for your gracious presence there. Thank you.